Hi everyone. This is the lecture for April for Physics 102, April 20th, 22nd, and 24th, and also for Physics 112, April 21st and 23rd. It's going to cover magnetism, and it is a combined lecture, but there is going to be more for the Physics 102 because there's a little bit of calculus, which I'm going to put into another video, which you'll watch on Friday. Okay, where is the material? Well, if you're Physics 102, if you log into our Moodle site and you go all the way to the bottom, you will see there at the very bottom there is a link for April 20th, 22nd, and 24th. Those are all the notes that I'm going to be going over in this video. And if you're Physics 102, again, log in and scroll all the way to the very bottom. And there you can see the notes for April 21st and 23rd. It's going to be a long video. I don't know how long it'll be because I haven't done it yet. But, all of these videos, um, you don't have to watch them all in one sitting, obviously. Watch as much as you can, and then just note the timestamp. And when you return to it, pick up from where you left off. Okay. It's very difficult for me to figure out exactly how much material is equal to how much time. This is not like the classroom. So I hope this is working out for you guys. Okay, so well, let's begin. So the entire lecture, or the entire video, is on magnetism, and we'll actually complete that by the end of this video, except for the extra calculus for the Physics 102 students. Okay, so if you remember magnetism, when we first started off studying electricity and magnetism, I said that there doesn't seem to be a relationship between electricity and magnetism. Okay, and that was indeed the case until the 1800s. And the reason is because there is no force between North and South Pole, and North and South Pole, that's for magnetism, and positive and negative is for charge. There is no force between positive and negatives and north and south poles. Okay, and that is if the charges are static, and by static that means they're not moving. Okay, so if you were to take a bar magnet here and you put it on a swivel, okay, basically that's like a compass, and you put a positive charge nearby, and you can even move it slowly, move the positive charge slowly around this. It won't attract or repel the north or the south. And same thing with the negative. Okay, so it appears that the two are different, but they're not. It took Alessandro Volta to invent the battery before we could discover what the relationship was between electricity and magnetism. And the reason is that the battery is able to is able to create a sustained current. Okay, and you need a current in order to create a magnetic field. All right, and so there's the relationship. It's not static charges that interact with magnets. It's currents that interact with magnets, and we'll see that as the video goes on. Okay, so this was actually discovered by Ørsted, and Ørsted, it was just in the middle of a lecture. He was just giving a lecture to some students in the early 1800s, in 1820, and he had a compass, and he had a wire, and he put current across the wire using the battery, and it deflected the compass needle. And he goes, "Oh, that's interesting." And he did it a few times, and that was it. That was the discovery. Ørsted discovered it, but it turned out that another physicist called Ampere was the guy who actually came up with a law that governs what the relationship is. Okay, and so we'll start off with Ampere's law. So I can't give you a full expression of Ampere's law. It not only requires calculus, but it requires vector calculus, which is beyond the scope of even Physics 102. But I can give you a very good idea of like what's involved in Ampere's law. I can give you some intuition, and also I'll give you the formulas for Ampere's law applied to two situations. One is a straight wire, and the other one is a coiled wire, which is known as a solenoid. Okay, and solenoids actually turn out to be very important for magnetism. All right, so let's start off with a straight wire. And so what we're seeing here is actually it's the same straight wire, but they're two different views. Magnetism has a lot of things which have to be drawn in 3 dimensions. Okay, and so you're going to see a lot of my diagrams will actually have a couple of views to try to get across what I'm trying to say there. So in this diagram where I have the side view here, you can imagine a wire, and it's just a straight wire here like that, and we're going to attach the bottom of the wire to the positive end of a battery and the top of the wire to a negative end of a battery. And what happens is as the current flows, you can see the current there, I, as the current flows from positive to negative, it establishes a magnetic field. And it's kind of surprising. The magnetic field is actually not parallel to the wire, but it circulates around the wire. Okay, and so to show you that circulation, I'm giving you here a top view. So this is actually the same wire, but now you see that that little circle with a dot in the middle. That's the wire coming straight at you. Okay, so it's coming straight out of the paper there. Okay, and the current's coming out towards you, and as a result, it actually establishes this magnetic field which circulates around the wire like that. Magnetic fields are called B fields. I don't know what the history of that is, but they're called B fields. And you can definitely see that there's a B field there, because if you take a compass, you'll see that the compass, the north and south of the compass, will align itself with the B field. And so I've shown the compass over on this side, north and south being aligned with the circulation of the B field this way. But if you move the compass to the other side, it'll turn. And if you had the compass over here, it would be that way. If you put the compass over there, it would be that way, okay, along with the field lines. And actually in one of the labs on magnetism, if you take a compass and you would have taken a compass and you would have moved it around the wire, and you would have actually seen that the B field is circulating. Okay, before I give you the formula for this, I have to tell you about the direction in which the circulation occurs. And because magnetic fields, they're chiral fields, they're kind of like they have a right-handedness to them. There's this right-hand rule, and it's actually applied in many different places. Okay, and there are different variations of the right-hand rule. And the way the right-hand rule works in this particular situation is you take your right hand and you point your thumb in the direction of the current. So you can see here, here's the current over here. The current is going up, so I'm going to point my thumb up. Okay, and you'll notice that my fingers curl around my my thumb, and they point in the direction in which the magnetic field is going to circulate. Okay, it takes a little bit of thinking about it, but just point your thumb in the direction of the current. See, my thumb is pointing up, and my fingers, they're going to point in the direction of the circulation. So if the wire is going up like this, the B field circulates like this. Okay, towards you, and then away from you, and then towards you, and so on. Okay, so it takes a little bit, but there's the right hand rule, and it describes the circulation of the magnetic field around the wire. What about an equation, though? Okay, so is there an equation that actually describes this? Well, I'm not going to give you the vector calculus form of Ampere's law, but it basically says something like this. It says, look, if you go around the wire and you just add up the B field as you walk around the wire, the sum of that B field multiplied by every little step that you take along the way. Okay, if you add up that B field multiplied by every little step, that's equal to the current going through the middle of the going through the wire. Okay, so applying Ampere's law to a straight wire, here's the B field. Here's the entire path as you walk around the wire. Okay, like that, and that's going to equal the current being carried by the wire. Like that, okay? And then there's also this other constant, mu naught, and mu naught is called the permeability of a free space, okay? So again, Ampere's law is you add up the B field as you walk around a wire, okay, multiplied by every little step. Now, if you're walking around the wire at some radius r, then you're etching out a circle of radius r, and the circumference of a circle of radius r is going to be 2 pi r. So here's the B field. Here is the total distance that you walked around it, and that's got to equal the current going through the wire, okay, multiplied by this constant known as the permeability of free space. Okay, if you rewrite this, it looks like that. and this is how we will use the equation, okay? So this is the B field generated by a straight wire, and it's equal to mu naught, the permeability of free space. I'll give you that value in a second, multiplied by I, which is the current, and divided by 2 pi r. Okay, so as you go further and further out from the wire, your R is going to increase, your magnetic field will decrease. Okay, if you have a bigger current traveling through the wire, well, then you're going to get a bigger B field. Okay, so bigger I, bigger B. The further you are from the wire, the smaller B. Makes sense. Okay, what is this permeability of free space? It's kind of the equivalent of epsilon naught. So if you remember when we were looking at capacitors, and I said you could build a capacitor by using two parallel plates, two parallel metal plates, okay? And you got an equation there, and in that equation you had this epsilon naught, and that was called the permittivity of free space, okay? And the permittivity of free space was kind of like a measure of how much empty space, what we call in physics the vacuum, it's how much empty space could sustain an electric field, okay? So electric fields can travel through matter, all right, but they can also travel through empty space. So, you know, empty space isn't without properties. And one of the properties of empty space is how much electric field can be sustained in that empty space. And that is what this epsilon naught measures. Well, guess what mu naught is? It's the equivalent of that, but for magnetic fields. It's a measure of the ability of the vacuum or empty space to sustain a B field, okay? And it has a value. And here's the value, okay? So like all of these constants, no one remembers them on a test. I would obviously give them to you like I did on the last test. And it's equal to 1.26 times 10 to the minus 6 Tesla meters per amp. Okay, so there's a new unit there. This unit, Tesla, all right? And when we do the Lorentz Law, you'll actually see and what a Tesla is a lot better than right now. But basically a Tesla is a measure of a magnetic field. So the unit, the MKS units of magnetic fields is a Tesla, okay? Meter, you know what that is, and an amp, you know what that is. So an amp, it's the measure of current, and that's like if you have so many coulombs traveling per second, that's your amperage, okay, or how much current is being traveled, is moving, okay? So this unit Tesla, like I said, I'll give you a better intuition into how big a Tesla is, how it relates to other things later. But right now, a Tesla, all you need to know is that it's a very big unit. Okay, typical magnetic measurements of magnetic fields in the lab are usually down in the millitesla range or even down into the microtesla range, okay? And of course the Earth has a magnetic field, so the Earth's magnetic field is down in the microtesla range, and it's between like 25 and 65 microteslas depending on where you are on the Earth, okay? So there you go. There's the wire, the magnetic field due to a wire. So we can do our first problem. It's pretty simple if you just plug into the equation. So how strong is the magnetic field? 1 centimeter from a wire carrying a 100 milliamp current, okay? So 100 milliamps is pretty easy to create in the lab, okay? And so we have this wire, and we're just going to put 100 milliamps of current through it, and we're going to measure the magnetic field about 1 centimeter from the wire, okay? And by the way, the instrument to do that is called a Gauss meter, and you should see that in the lab. All right, so R is basically 1 centimeter, or we have to work in MKS units, so it's 0.01 meters, and the current is 100 milliamps, but we got to convert that to amps because we got to work in the MKS units for current, and that's amps, not milliamps. So 100 milliamps is 0.1 amps, all right, and we just plug that into the equation above. So there's that mu naught multiplied by the current, divided by 2 times pi, so there's 2 times pi, and there's R, and it works out to be 2 times 10 to the minus 6 Teslas. 10 to the minus 6, that's micro, so it's 2 microteslas. So that's pretty small. It's actually smaller than the Earth's magnetic field, okay? And so you would barely be able to deflect a compass with this, all right? So you really, to get any kind of like deflection of the compass in the lab, you're going to have to do things up into the several amp range, okay? And when you're putting like a couple of amps through a wire, um, it gets a little dangerous because the wire can heat up pretty quickly, okay? And it can actually, wires are usually made out of copper, but they can get up hot. It can get hot enough that it'll actually melt the copper and cause sparking and stuff like that. So, yeah, like if you're talking like moderate currents, like 100 milliamps, and you're only measuring at 1 centimeters distance, you're not getting a lot, okay? I'll show you how to make more powerful magnetic fields in a little bit. Okay, so there's the magnetic field due to a wire. Okay, but I told you that there was another shape and that we were going to study, and that's basically a coil of wire. Okay, and so we can also apply Ampere's law to this coil of wire. Again, the mathematics is very complicated. I won't go through how Ampere's law actually gives you the formula that we'll use, but if it's doable. So what you're seeing here in this picture is basically a coil of wire. Now it's hard to draw a coil of wire in 3 dimensions. So what you're looking at here is here's the positive end that's attached to the positive end of a battery. This other side is attached to the negative end of a battery. And what we have here is a coil of wire, and you can see here this part here, when it's going down, that's towards you, that's close to you, that's like the front of the coil, and then it goes towards the back. I know it doesn't necessarily look like that, but I tried to indicate that. You see how there's a little break in that wire? It's not that the wire is broken, it's that it's going behind the other wire. So I'm trying to give you a sense that this is the front and this is the back of a coil, of one of the loops in the coil. And so here we go again. Okay, so down here there's the front, and the current is going down in the front, and it's going up along the back, and then down in the front and back, and like that. Okay, so this coil of wire like that is called a solenoid. All right, and they're very important in mathematics. And there's a right hand rule for this too, but this right hand rule is slightly different than the previous right hand rule. It turns out that the two are equivalent, but for a solenoid it actually makes more sense to have your fingers point in the direction of the current. Okay, so you can see your fingers are going to curl around like that, and then your thumb will point in the direction of the magnetic field. So in this particular case, what you have is, orienting my hand like the diagram there, you have the current going this way. It's coming down towards me, and so the magnetic field would be to my right. Now, if I turn my hand around so that you see it that way, here's the current coming down in the front there like that, and you can see my finger is going to point in the direction of the B field. Okay, so again, this is a slightly different variation of the right hand rule. In this case, for the solenoid, you point your fingers in the fingers of the right hand, you point them in the direction of the current, and your thumb will point in the direction of the B field. Okay, and so you could see here that you'll actually generate this B field. So I only drew one vector for the B field going right through the middle of the solenoid like this. And if you were to put a magnet here, you would see that the south side of the magnet would be attracted to this, and the north side would be attracted the other way. Okay, so that's the way a magnet actually orients itself in a B field. The north is on the side where the arrow is pointing, okay, and the south is on the other side. Okay, if you were to put the magnet on the other side, well, then it would the north would be pointing, still in the same direction, and the south would still be pointing in the same direction like that. Okay, and so well, this is a solenoid. Okay, and the reason solenoids are very useful in magnetism is because the solenoid is actually concentrates the magnetic field inside the coil. Okay, it's not that there isn't a magnetic field outside the coil, but what happens is outside the coil the magnetic field kind of flares, and I tried to draw that in this diagram here. Okay, and so you can see that inside you get the B field, and I drew quite a few vectors in there indicating the B field. But when it exits out the mouth of the solenoid, then it kind of flares around, and the B field then circulates around here like that, and then comes back like that and goes through the middle. All right, inside the solenoid, the B field is uniform. Okay, so it's not like it's stronger on one end or the other. Okay, only at the mouths does it begin to flare out. So if you're definitely inside the solenoid in here, the B field is some constant value, and it's always pointing in the same direction. Okay, so it's uniform in direction and constant in magnitude. All right, and that's actually kind of like what we found with the capacitor. So in many ways, the solenoid is the equivalent, the magnetic equivalent of a capacitor. So you remember with or a parallel plate capacitor, I should say. So you remember with a capacitor, if we took one metal plate here, okay, so this doesn't look like a metal plate because you're looking at it edge on, but you know, if you here's your metal plate, okay, it's looking at it edge on. So we got one metal plate there, and that's positive, and another metal plate below it, and that's negative, like that, okay. And inside the capacitor, the electric field was again uniform direction in the way I drew it there. It's downwards, and it was always constant magnitude, okay. And so um, there's the solenoid, which gives you a uniform constant magnetic field in the middle, and there is the parallel plate capacitor, which gives you a uniform constant electric field in the middle. At the edges, the electric field will flare for the capacitor, and the magnetic field will flare as well for the solenoid. Okay, but this is what makes them very useful because like vector calculus is very difficult, and so if you have a uniform vector field, that's very easy to work with. Okay, so there it is. Now, that tells you the direction, the right-hand rule. But what about the formula? Well, again, I can't go through the Amperes law with all the integration and all that. I'll just give you the answer, and here it is. The magnetic field inside the solenoid, not on the outside, is equal to, once again, that mu naught, this permeability of free space, multiplied by n divided by L, where n is the number of windings for the solenoid and L is its length. Okay, and so N over L is kind of like the density of the windings. Like if you have more windings over a shorter length, then you have a higher density here. Okay, so this is kind of the density of the windings per unit length, and then of course multiplied by the current. Okay, and this makes sense. Okay, the more like for every time you make a loop, it's like you're doubling. Like if you have one loop, well, then you have so much current. If you have two loops, then you've doubled the current, okay, through those two loops. And then if you do it three times, you triple the current. So of course, the magnetic field is going to go as the number of windings you have, because each time you add a winding, you're adding another loop of current. It also goes as the current. Okay, and it's inversely proportional to the length, because the shorter the length, the more you've concentrated that current into a shorter length, and the more magnetic field you get. Okay, so those are the three ingredients that go into your magnetic field. Once again, the more windings, the bigger your magnetic field. The bigger your current, the bigger the magnetic field, and the more you've compacted it together into a short solenoid, the bigger the magnetic field. Okay, so great. And so now we can do a little problem. Oh, not quite yet. Sorry. I told you earlier that we can make really big magnetic fields, and the solenoid is how you do it. But you can actually make it even better than just having a coil of wire. You can take this coil of wire, and in the middle of the coil of wire, you can add what's known as a ferromagnet, some ferromagnetic material. Okay, and a ferromagnetic material is just any material which is magnetizable. Okay, this is kind of the equivalent for the parallel plate capacitors, where you had that dielectric, and the dielectric was polarizable and it enhanced the capacitance. Here you have a ferromagnet, and the ferromagnet is magnetizable, and it will enhance the magnetic field. Okay, so you still have a solenoid, and you can see here that I'm trying to wrap this solenoid, this wire, around some tube here, or not a tube, but a cylinder, and the cylinder is just some ferromagnetic core. So what are typical ferromagnetic materials? Well, anything that a magnet will attract, like iron, nickel, zinc. Okay, these are all things that are magnetically attracted. Examples of things that are not ferromagnets, that are actually diamagnetic, are things like aluminum. Okay, so you wouldn't want to put aluminum in the middle, but a nice iron core will definitely enhance the magnetic field for a given current. And then the equation changes ever so slightly. It's still the same as above, but it's got this extra mu r, and that mu r is the enhancement of the permeability. okay, because of the presence of the ferromagnetic material. And this mu r is just called the relative permeability, okay? And so it's just an enhancement, and the number is usually bigger than 1. I mean, you wouldn't want to use a number smaller than 1 because it would like decrease the magnetic field. You use something which enhances the magnetic field, okay? And so I'm going to show you in the next example that we can make quite a strong electromagnet using a solenoid wrapped around a ferromagnetic coil. Okay, and so the relative, so here's my example here. The relative permeability of ferrite, which is nickel plus zinc, okay, is 2,300. It's a dimensionless number because it just says by what factor is the magnetic field increased. And so by putting this nickel zinc core inside the solenoid, it's actually going to increase the magnetic field by 2,300 times. And so that's pretty good. Okay, so we're going to use it as a core in an electromagnet made with 1,000 windings of wire over a length of 5 centimeters. Okay, so our solenoid's only like 5 centimeters long, like that, and we have 1,000 windings of wire around there. And you know what, when you make these things, like, you don't have to like do uniformly. You could go over them back and forth like this, you know, like you could have several layers of windings. Okay, as long as they're all turning in the same direction, that's fine. Okay, and then we're going to put 3 amps of current through this wire. Okay, and I want to know how much of a magnetic field does this generate. And it's kind of surprising. So here we go. I'm just plugging into to this equation right here. Okay, so we're just going to plug into that equation. For mu r, we're going to plug in 2,300. For mu naught, we're going to plug in that value that I gave you earlier. For n divided by L, well, n is the number of windings, which is 1,000. L is going to be what I say, 5 centimeters, like that, and I is going to be 3 amps. Okay, so it's a very simple little formula there, like that, and we plug in, and we get a whopping 174 Teslas. Okay, that is quite extreme. Okay, you know, like you definitely be able to pick things up with this thing. All right, so there you go. Now, what if we didn't have that ferrite in the middle, that ferromagnetic material? Well, if you do this again, but you get rid of that 2,300, well, then you only get 75.6 milliteslas. Okay, so in reality, like if you were doing this, like 3 amps is really big. Okay, you wouldn't be able to sustain this for a long time. So it's really that 3 amps which is making this number very big. But you know, if you're down in like maybe 100 milliamps or 10 milliamps, you know, that's something which is doable. You know, that would certainly decrease this number. Okay, so say it's like instead of 3,000 milliamps, which is what 3 amps is, you cut this by a factor of 100 to just like 30 milliamps. Well, then you would get 1.7 Teslas, which is still a very big field. Okay, and that would be very doable in the lab. All right, so there you go. This is the story of Ampere's law and how you can get a magnetic field generated not from static charges, but from moving charges. And another name for moving charges is a current. Okay, and so that's why for the longest time, at least until the 1800s, well, until 1820, when Ørsted discovered this, we didn't know that there was a relationship between electricity and magnetism because all we had was static electricity and we had magnets. Okay, in fact, the word for electricity, electron, is the Greek word for amber. And so as way back, as far back as the Greeks, they knew about static electricity because they would just rub amber, and amber would, you know, acquire a static charge. And then they also knew about magnets because magnets come from a mountain called Magnesia in Greece, and so they knew about magnets. But they didn't, you know, I don't know if they played with them, but they wouldn't have noticed that one attracts the other. No, it took Volta to invent the battery, which gave us long-lasting currents. And then once we had those long-lasting currents, then you could say, oh, a current will deflect a magnet, and ta-da, that's how we discovered that currents actually create the magnetic fields, and then Ampere's law. Okay. So there's the story with currents creating magnetic fields. But what do magnetic fields do? Okay, so you know that an electric field will cause a charged particle to accelerate, either collinearly or against the electric field, depending on either with or against the electric field, depending on whether the charge is positive or negative. But what do magnetic fields do? Okay, well, implicitly, you know that they deflect magnets, but that kind of just begs the question: what is it about the magnet that the magnetic field causes an interaction? And that's what this Lorentz force is. So magnetic fields do exert forces on charges, but once again, magnetic fields don't exert a force on a static charge. Magnetic fields exert a force on moving charges, in other words, currents. Okay, so this is kind of interesting. You need a current to create a magnetic field, and then once you have a magnetic field, that magnetic field will exert a force on moving charges, not on static charges. Okay, so electric fields do. Okay, once again, if you have an electric field and say the electric field is up or down and you put a charged particle in it, so say the electric field is up, you put a positive particle in that electric field, it'll accelerate up because it accelerates with the electric field. If you have a negative charge and you put it in an electric field and the electric field is up, then the negative charge would accelerate in the opposite direction of the electric field. But how do magnetic fields work, and how do they exert forces on moving charges? And the answer is the Lorentz force. Okay, and the Lorentz force, this gets a little bit difficult to picture. Okay, the Lorentz force is interesting because it's not with or against the magnetic field. It's actually perpendicular to it. Okay, and so that's what makes magnetic fields kind of hard. This right-hand rule appears over and over and over again. And so to show you the direction of the Lorentz force, before I even give you the equation, imagine that you have here a positive charge. So here's a positive charge Q, but it's not standing still. If it were standing still, it wouldn't even know that there's a magnetic field there. It just would not experience anything. Now this charged particle is moving with a velocity v like that. Okay, and it's moving with a velocity v, and it cuts across these B field lines. Okay, so the magnetic field is going off to the right. Okay, and the charged particle is cutting across them at some angle theta, like that. All right, what happens? There's a force on the charged particle. Because the charged particle is moving through the magnetic field, it experiences a force. What direction is the force? And this will surprise you. It's actually directly out of the page towards you. Okay, so the Lorentz force, which is the force that a magnetic field exerts on a charged particle, is actually perpendicular to both the B field and the velocity. So let me say that again. The force that the magnetic field creates, this so-called Lorentz force, okay, the force is going to be perpendicular to both B and V. And you say, well, how can that be? How can you have a force which is perpendicular to both of them? Well, there's only one way, and it's got to be out of the page, either out of the page or into the page. Okay, so there's two possibilities, and the answer is it's out of the page, and that's where this right-hand rule comes in again. So this is yet a third variation of this right-hand rule. Okay, and so the way it works is, well, I guess I need to show it to you in this diagram here. The way it works is, what you're going to do is you're going to take, oh, I guess I have, no, so 1 second here, I have a diagram below. Yeah, I'm sorry, here it is. Here's the diagram below. The way this right-hand rule works is you take the velocity vector, which in this particular diagram I have coming out towards you. Okay, so you start with the velocity vector and you imagine rotating the velocity vector towards the B field. Okay, so you start with V, and just like imagine like it's the hands of a clock, it's going to rotate towards B. Okay, so you can see here I have theta, but I don't just have theta, I have theta with a little arrow on it because I'm rotating from V to B. What you do is you take your right hand and you point your fingers in the direction of the rotation. Okay, so V is rotating towards B, and your thumb will point in the direction of the force. Okay, so there it is. That's well, there it is for a positive charge. Okay, so once again, start from V, rotate it towards B, point your fingers in the direction of the rotation, your thumb will point in the direction of the force. If it's a positive charge, that's the direction of the force. If it's a negative charge, then you've got to do one other thing. You've got to change the direction it would be in the opposite direction. Okay, I think I might have gotten it wrong up above. I think I said the force was directly out of the page. Actually, it's into the page here. Okay, so we can practice the right hand rule here. So imagine you have this velocity v here, and you're going to rotate it to b. Now, if you're rotating from v to b in this diagram, you're actually rotating clockwise. So you're going to aim your fingers clockwise like this. See how my fingers are clockwise like this? And my thumb would be pointing into the page. Okay, so in this case the force is actually into the page because it's a positive charge. If it were a negative charge, then the force would be out of the page. Okay, so out of the three variations of the right hand rule, this is by far the hardest. Okay, so let me just re-summarize because it's kind of hard to get your head around. Okay, B fields exert a force on moving charges. Okay, they exert a force on, not on static charges, but on moving charges. The charge here, Q, is traveling with a velocity v, and it cuts across the B field with some angle theta. Okay, the direction of the force is perpendicular to both v and b. Okay, and so it's either into or out of the page here. And the way you determine which of the two it is, you rotate from v to b. Point your fingers of the right hand in the direction of the rotation, and your thumb will point in the direction of the force if it's positive, and if it's negative, you have to flip the direction. Okay, now that tells you the direction. What about the actual formula to calculate the magnitude of the velocity? And here it is. Okay, so there's quite a few ingredients here. The bigger the charge, the more force there's going to be. That makes sense. Okay, so more charge, the more electrical substance there is for the electric field to interact with. Okay, so the bigger Q is, the bigger F is. The faster the charged particle is going, the bigger the force is. That also makes sense. In fact, if V were zero, if there were no velocity, then the force is zero. So that's actually, one of the points about how the magnetic field interacts with a charged particle. If there's no velocity, there's no force. Okay, so the bigger the velocity, the bigger the force. Okay, the bigger the magnetic field, the bigger the force. All right, so all of that makes sense. But then there's also this other piece, the sine theta piece. Okay, and the sine theta says that the force depends on the orientation between V and B. So let's look at our diagram again. Okay. And what you're seeing here is the velocity is up this way and the B field is that way, and there's an angle there. Okay, looks like around roughly 30 degrees. So actually here you would have sine of 30 degrees, which is a half. All right, if the velocity were perpendicular to the B field, so that the velocity is actually cutting directly across the B field, then theta would be 90, and sine of 90 is 1. That's when you get your maximum force. But what would happen if the velocity were right along the B field, okay, so that both of them are collinear, okay, both V and B point in the same direction, or the opposite direction. You could have B pointing one way, and you could have V going 180 degrees the other way. Well, sine of 0 or sine of 180 degrees are both 0. You get no force. Okay, so if the velocity, just because a charged particle is moving, doesn't mean the electric field, the magnetic field is going to interact with it. If the velocity is actually right along the lines of the B field, there's also no force. It actually has to cut across them. Okay, and so scroll down. Oops. No. I'm sorry, guys. Scroll down here. That's what that sine theta is right there. Okay. So once again, when the charged particle actually cuts directly across the B field at 90 degrees, that's when you get your maximum F. When it's either along it or in the opposite direction, then you're going to get sine of 0, sine of 180, which is 0, and you're not going to get any force. By the way, we saw this earlier in the course with torques. Okay, so this is kind of similar to torques. All right. All right. Now, that's the story of the Lorentz force if you've got a charged particle. But what if you have a wire carrying a current? Okay. And a current Don't forget, a current is just is moving charge, is either one moving charge or many moving charges. And so we can actually recast the Lorentz force in a slightly different form, which is useful in situations where you have a wire carrying a current. And the way we do that is we start off by looking at the velocity. So the velocity is equal to L divided by delta T, where L is the length of the wire that is actually going to be inside of the B field, okay? And so suppose it takes a charged particle a time at delta T to travel that distance L, okay? So it's got to travel this charged particle. It enters the B field inside the wire, and then it exits the B field outside the wire, and it travels a distance L inside of the B field, and it takes a time delta T. Well, if you travel a distance L in times delta T, that's a velocity, okay? Like that. And so now for our velocity, we can rewrite that as L divided by delta T. So this is the Lorentz formula from above, but I took out V and I wrote it as L delta T. Now let me take this delta T and put it under the Q like this. And now if you have a charge Q traveling through that wire in time delta T, charge per unit time, that's current, okay? And so here's a completely equivalent way of writing the Lorentz force, but this one is more appropriate for a wire inside of a magnetic field, whereas the previous one was more appropriate for a charged particle, like a proton or an electron moving through a magnetic field. Here we're actually going to have a wire traveling through the magnetic field, okay? And so how does this go? Well, the bigger the current through the wire, the bigger the force. That makes sense. If there's no current, you're not going to get any force. And so it's a linear relationship. The longer the wire inside the magnetic field, and I got a diagram in a second, the longer that wire in the magnetic field, the more force there is, because the magnetic field kind of exerts so much force per unit length. And so if you have more length, you'll have more force. So the longer the wire bathed inside the field, so it's not just the length of the wire, but it's the length of the wire that is inside the field, okay? So the longer that is, the bigger the force. Of course, the bigger the magnetic field is, the bigger the force. And once again, we have that sine theta because the orientation of the wire and the magnetic field is important, okay? And so we're ready to do a problem, okay? So let's do a problem here. Let's take the Earth's magnetic field. So at the Earth's magnetic field at a certain point is 50 microteslas, like that, okay? And a wire carrying a 1.5 amp current cuts across the field at a 30-degree angle. Okay, so the wire and the magnetic field, they're not perpendicular, they're actually at 30 degrees to one another. Okay, and I want to know what is the force on the wire per meter length. Okay, per meter length. And then I say repeat this, but assume that the wire is actually parallel to the magnetic field. And this is not a hard experiment to do, actually. You know, you've got your wire and you can just move it around. And you can move it around in different, put it in different orientations in space. And when you've got these different orientations in space, you're going to have a different force per unit length because you're going to cut the magnetic field. The wire is going to cut the magnetic field at different angles. Okay, so the first part is 30 degrees. So how does that work? Well, we're not talking a charged particle. I'll do an example of that in a minute. But we're not talking a charged particle here. Rather, we're talking a wire. So it's more appropriate to use this particular form. F is equal to ILB sine theta. And I asked you to do it per unit, per meter. So let's just assume that we have 1 meter of wire. Okay, so 1 meter of wire inside of the Earth's magnetic field. So we'll set L equal to 1 meter. Okay, and so it's just as simple as plugging in the numbers. Your current, I told you, was 1.5 amps. Your length is 1 meter because we want to look per meter. Okay, the magnetic field, I told you, was 50 microteslas. Micro is 10 to the minus 6, so 50 times 10 to the minus 6 teslas. And you work this out, and it turns out to be a really tiny number, okay? Only 37.5 micronewtons, or 3.75 times 10 to the 5 newtons per meter. So a meter of this wire would barely feel any force on it, okay? Nonetheless, you know, it's measurable, but it would be very, very tiny. Now, at this point, we can actually analyze the units and you get a better idea of what a Tesla is than what I gave you above. Okay, so if we do an analysis of a unit analysis of uh, uh, the Lorentz force, here we have force. What's that equal to? It's equal to current times length times your magnetic field, the sine theta that doesn't have any units. Okay, and so we know that the units of force are newtons. We know that the units of current are amps. We know that the length of the wire, or the length of of the wire bathed, is meters. And so we get a unit for the magnetic field Tesla, which is equal to a Newton per amp meter. And you go, what does this Tesla equals a Newton per amp meter? How should I interpret that unit? And the way you can think about it is that a 1 Tesla field will produce a 1 Newton force per meter of wire for 1 meter of wire carrying 1 amp. Okay, then that's assuming, of course, that the wire is cutting the field at 90 degrees. All right, so let me say that again. If you have a 1 Tesla field, okay, it will produce 1 Newton of force for 1 meter long wire carrying 1 amp. You have a wire, it's 1 meter long, it's carrying 1 amp, and it's in a 1 Tesla field. It'll have 1 Newton of force on it. That gives you another way of thinking of what a Tesla is. Okay, so and by the way, Tesla, it was named after Nikola Tesla, who was a famous engineer at about 100 years ago. Okay, so part B, if you remember in part B, I said, well, we're going to have the same situation, but now I want the wire and the field lines to be parallel to one another. But parallel means that theta is equal to 0 degrees, and sine of 0 degrees is 0, and so that means there's no force. Okay, so here's my diagrams that I'm trying to show you the two different orientations. When you have the wire perpendicular to the B fields, that's when you'll get your maximum force. But if your wire is actually parallel to the B fields, there's no force, none at all. Okay, and that's just the way these B fields work. All right. So we're going to do another problem, because that problem was with a current. Let's do a problem with actually a charged particle. Okay, and just to be kind of realistic, the northern lights are actually charged particles. Okay, so the aurora borealis is due to these charged particles, and what happens is the charged particles get trapped in the Earth's magnetic field, and they actually spiral. You'll see that in a second, why they spiral. And they spiral, and actually because of the shapes of the Earth's magnetic field, they spiral, but they also spiral and they're kind of funneled into our atmosphere. And when these charged particles, which are traveling pretty fast, they're electrons, protons, and things like that. When they hit our atmosphere, they ionize our atmosphere and they cause it to glow. That's what the northern lights are. Okay, so I actually looked up some numbers. Okay, and the problem that we'll do in a minute, we'll actually use numbers from the aurora borealis. Okay, but a minute ago I said that these charged particles would spiral, and you're wondering, well, why do they spiral? Isn't that kind of like going in a circle? That's right. You'll be surprised that when a charged particle enters a magnetic field perpendicular to the field, okay, it actually undergoes uniform circular motion. All right, so that's kind of interesting. It's the charged particles. They don't just get deflected by the field. They go in and they do get deflected by the field. I shouldn't say that, but they don't get deflected just once. They keep getting deflected, and they keep getting deflected in such a way that they're always going in a circle. Okay, and so that's what's happening when these charged particles from the solar winds get trapped inside of our magnetic field, the Earth's magnetic field. They start to spiral. They start to loop like that. Okay, and why? Why do they do that? And so that's what this diagram is trying to show. And again, all of these diagrams are really hard to draw because and even hard to picture because everything is in 3 dimensions. Okay, so here I have magnetic field vectors, and you say, where are they? Each one of these circles with the little dot is an arrow pointing out towards you. Okay, so imagine that the B field, the magnetic field, is pointing straight out of the page. It's pointing straight out of the page. Okay, and what we're going to do is we're going to fire a charged particle into it. And just to make it easy, because positives will spiral one way, negatives will spiral the other way. Let's just do a a positive charged particle. So here's the positive charged particle. It's traveling in the plane of the paper, and it enters our magnetic field, and the magnetic field is out towards us. Okay, now use this right hand rule. It's a little hard, but let's think about it. The V is up and the B field is out towards us, so we want to turn from the V field in the plane out towards you. Okay, so we want to turn it this way. Okay, so here's the V up, and we want to turn it towards you. Think of that kind of a circulation. So point your fingers in the direction of the rotation from V to B, and your thumb is going to point that way. So as the charged particle enters the B field here, and its velocity is up, and the B field is towards us, the force is actually going to be towards the right. Okay, the force is perpendicular to the velocity, as it has to be. It has to be perpendicular to both. Well, what happens if there's a force to the side? This charged particle is trying to move ahead, and this force is turning it. And so guess what? It starts to turn. But as soon as it starts to turn, suppose it's turned to this point, well, now the velocity is this way. The velocity is towards the right, and the B field is up. Again, if you curl the velocity to the B field, now you find that the force is down, like this. And so the force is always perpendicular to the velocity, and that makes it turn. The force will always point towards the center of uniform circular motion. Okay, so that's what happens when charged particles enter magnetic fields. They undergo uniform circular motion. Okay, and the force is always perpendicular to V, so the acceleration is always perpendicular to V. And whenever you have velocity and the acceleration perpendicular to the velocity, the acceleration is not speeding it up or slowing it down. It's always turning it. It's always turning it. It's always turning it. And that's uniform circular motion, okay, that we studied last semester. All right. So actually, you can calculate a frequency here. You can calculate the frequency at which these charged particles rotate. Like how many times do they make a rotation per second? And that's an interesting frequency because it's called the cyclotron frequency. And actually they generate radio waves, and you can actually hear those radio waves. Or you can't hear them, but you can pick up those radio waves. Okay. And so let's calculate the cyclotron frequency that of charged particles in the aurora borealis. All right. So that's my next problem. Okay. Find the cyclotron frequency and radius of the uniform circular motion that an electron traveling at 800 kilometers per second. That's how fast the solar winds are. They're 800 kilometers per second, which is really fast. Okay, so so once again, find the cyclotron frequency and the radius of the uniform circular motion of an electron traveling at 800 kilometers per second when it enters the Earth's magnetic field, which is about 50 milliteslas. Sorry, microteslas. Okay, and so it may seem like, how do I do this? But let's just do it one step at a time. The first thing is, let's find out the Lorentz force. Okay, and now we're going to use this form of the Lorentz force. Okay, because this is the one that's more appropriate for charged particles. So we got QVB sine theta. All right. And we're just going to plug in the numbers. For theta, let's assume, like you don't know at what angle, the solar winds hit our magnetic field, and they hit it all different directions, so a lot of different things can happen. But let's assume for this particular problem that the electron is actually hitting the B field at 90 degrees, okay? And so the electron enters perpendicularly, and that means that theta is going to equal 90 degrees, and sine of 90 degrees is 1, okay? So that makes life easier. So basically the sine theta here, we don't have to worry about that. That's just going to equal 1. What's Q? Well, it's the Q, the charge of an electron, and you can look that up. It's actually negative 1.6 times 10 to the minus 19 coulombs. You've seen that number before, but we're not going to worry about the sign because the sign is just about the direction. Okay, and I'm not even worried about the direction in this problem. Okay, but basically to determine the direction, you would use the right hand rule, determine the direction of the force, but it's negative, so you flip the direction, okay? Again, we're not worried about the direction here, so I'm not worried about the sign. So the charge of an electron is negative 1.6 times 10 to the minus 19 coulombs. Not worrying about the sign there. The velocity is 800 kilometers per second, but we have to work in MKS, so that's 800,000 meters per second, or 8 times 10 to the 5 meters per second. The magnetic field is going to be 50 microteslas, which is 50 times 10 to the minus 6 teslas, or 5 times 10 to the minus 5 teslas. You put that all in there, and again, don't forget the sine of theta here is 1, so don't worry about that. You put that all in there, and you get that the force on the electron due to the magnetic field is 6.4 times 10 to the minus 18 newtons. That's a very tiny force, but electrons are very tiny. Okay, now that's the force. And to use the equations for uniform circular motion, which you may have forgotten from last semester, so you'll see them in a second. But to use those equations, we don't want the centripetal force, we want the centripetal acceleration. And how do you get acceleration from force? Just divide by the mass, okay, Newton's second law, okay? And so the Lorentz force is the centripetal acceleration in this case. It is, or the centripetal force, it is the force that keeps this thing on a circle. And so the centripetal acceleration is just going to be the Lorentz force divided by m. We just calculated this number, 6.4 times 10 to the minus 19, divided by the mass of an electron. And the mass of an electron is 9.11 times 10 to the minus 31 kilograms. Okay, I didn't write the units in there, but these are in MKS. Okay, again, I would not expect you to memorize that number. You would get it on a test. Okay, and we did see this number in one of my previous videos. All right, so if you work this out, and the way I like to do these, by the way, is just to show you, is I'll take like 6.4 and divide it by 9.11, and that gives me 0.703 here. And then I'll take the 10 to the minus 18 and divide it by 10 to the minus 31. Well, 10 to the minus 18 divided by 10 to the minus 31 is minus 31, which is plus. So the exponent here is going to be 31 minus 18, or you get, basically working this out, 7.03 times 10 to the 12 meters per second squared. Okay, now think about that. That is 10 to the 12. That's like a trillion meters per second squared. What's the acceleration due to gravity? Only 10. And this is like a trillion meters per second squared. So this tiny electron, because it's very light, it's not experiencing much force, obviously, but it is, because it's so light, it's experiencing a tremendous amount of acceleration. And now here we're going to use one of the formulas for uniform circular motion. And if you remember this one, A is equal to V squared over R. So you remember from last semester, like if you're in a car and you're going around a corner, if the corner has a radius R and you're traveling out a velocity V squared over R will tell you what your centripetal acceleration is. And that's why when you're going around a corner, you feel like, you know, you're being thrown out from the center of the turn. Okay, so we know the acceleration. We just calculated that. That's that 7 times 10 to the 12 meters per second squared. What we want to find, though, is the radius, because that was one of the questions. One of the questions was the radius, and the other one was the cyclotron frequency. So, you know, I'm just rearranging this equation. If I multiply and divide, multiply by R and divide by A, I get this rearrangement. And now V is the velocity of the charged particle. If you remember, it's that 800 kilometers per second, but converted to MKS. So there's the velocity of the solar winds divided by A, which we just calculated. And doing the same division like I do before, it turns out to be 9.1 times 10 to the minus 2 meters, or 9.1 centimeters. Okay, so these charged particles, you know, they're zipping around very fast, but you know they're basically going in a loop around that big. Okay, about 9 centimeters in size. Okay, that's kind of cool. All right, so that's what's happening in the aurora borealis. The electrons, I should say. I shouldn't say charged particles. The protons would be a very different radius because they have a very different mass. Okay, all right. So that's the radius. You can even call it the cyclotron radius, but we wanted that cyclotron frequency because that's actually something that's measurable. And here's another equation. This equation here is the equation for. Oh, whoops. Sorry, guys. All right, so this equation here is also an equation for uniform circular motion, but this one relates the velocity the radius, and the period of the motion. The period of the motion is the time it takes for one loop, and the frequency is just the reciprocal of the period. Okay, so when we did this, we were more worried about the period, so we only worked with capital T. But once you get capital T, the period, 1 over capital T is the frequency. Okay, so we're going to solve for capital T. And so just rearrange this here. You get that T is equal to 2 pi r over V. Substitute in all the numbers that we have above, and you find that it's 7.14 times 10 to the minus 7 seconds. Okay, that is a very short time. Yeah, the electron is doing a loop, which has a radius of about 9 centimeters, or a diameter of about 18 centimeters. Okay, but it's doing it extremely fast. Okay, so this is like 10 to the minus 7. If I move the decimal over like 0.7, that would be 10 to the minus 6. So we're down into the microsecond range. Okay, now the frequency, and this is linear frequency obviously, is just 1 over the period. So substituting that in, we find that that's going to equal 1.4 times 10 to the 6 hertz. Okay, and 10 to the 6 is mega, and so this gives us a frequency of 1.4 times 1.4 megahertz. Okay, and if you're wondering where is megahertz, that's just a little bit, that's actually within the AM range. Okay, so if you were under the northern lights and you're tuning your radio through the AM range, you're going to hear a lot of static, and that static is exactly all that cyclotron frequency from the aurora borealis being picked up by your radio in your car. So the AM range is like from 540 kilohertz to 1700 kilohertz, but 1700 kilohertz, that's like 1.7 megahertz, and so 1.4 megahertz, it's right in there. Okay, so there you go. There's the cyclotron frequency for electrons in solar wind being captured by the Earth's magnetic field. All right, so there's one tiny mystery before we move on to the next subject in magnetism, and that is we know that B fields are created by currents, and we know that B fields exert forces on currents. But what is this north and south then? Okay, in fact, when Ørsted first discovered that currents create magnetic fields, he discovered it precisely because the magnetic field interacted with a magnet. He didn't know that magnetic fields actually interact with moving charged particles. Okay, Ampere actually discovered that later. Okay, and then Lorentz gave it the form that we just studied. All right, but what is this north and south pole? Like, is this something else? Like, how does north and south relate to anything I said before? Well, here's the thing. Microscopically, if you take a look inside of ferromagnetic materials, what you find is that there is a bunch of looping electrons. Okay, that these electrons, they're usually the f orbitals of these electrons, they're making these loops inside of the magnet. So if you have a magnet, which is basically something like iron, but it's not just iron where the atoms are all scattered in every direction. This is iron where the atoms are actually all aligned like this. And their alignment means that the electrons, as they circulate inside of them, they're forming the little loops. Okay, they're actually forming something like a little solenoid in there. And so each little loop has its own north and south, and it adds to the neighboring north and south, and adds to the neighboring north and south, and that's what a magnet is. So there really isn't a north. Like, north isn't a thing, it isn't a substance. Like charge is a substance. North is not a substance. It's just one side of a loop of rotating current. Okay, and south is the other side. All right, and if you remember, I said to you that charged particles can be separated. So if you have like a hydrogen atom is made out of a proton and an electron. Okay, and it's totally possible. It's called ionization. You just take the electron and you move it way off over there, and you take the proton, you may move it way off over there, and now you have the charges separated. The negative is way off on one side, the positive is way off on the other side, and the charges are separated. But you can't separate magnets, north and south in magnets. You remember that if I have a north and south magnet and I break it, what I wind up getting is two magnets, both of them with their own north and south. And so you can't separate north and south. And you go, well, why? Why can't you do it? Now we know why. And here's why. Because there's two sides of a loop. And you can't have a loop which just has only one side. You know, every loop is going to have a one side and then the other side. And if you use the right-hand rule, so you can see here what I tried to do was I tried to show this looping. So this is a current. Okay, this is a current making a loop here, and this side here, the thicker side, that's supposed to be closer to you, and the thin side there, that's the far side, that's supposed to be farther from you. Okay, so you see that this, you know, let me see if I can animate it here. It's kind of like this, all right. And if you point your fingers in the direction of the current, your thumb is going to point in the one direction. Okay, that's the direction of the B field. That's the north side of the loop. And of course, the other side is the south side of the loop. And, you know, like, I mean, it's unimaginable. How can you have a loop which has one side but not another side? I mean, that makes no sense. So that's why north and south always come together, because they're really not substances. Like, you know, an electrical substance. Okay, there's no such thing as a magnetic substance. All they are is they're just two different sides of the circulating current. Okay, so there you go. That's magnets. And so now when you're looking at those magnets, you could say, oh, that magnetic field, it's not so much that it's interacting with the magnet as it is it's interacting with the circulating electrons within the magnet. In other words, it's exerting a Lorentz force on the electrons inside the magnet, and that's what causes the compass needle to deflect in the presence of a current. Okay, the current in say a straight wire generates the magnetic field, and the magnetic field then that's Amperes Law. So the current in the straight wire generates a magnetic field. That's Amperes Law. And then that magnetic field exerts a force on the circulating current inside the magnet, and that's the Lorentz force. Okay, and that's what turns the compass in the presence of a current. Okay, that's what Ørsted discovered. All right. Next topic in magnetic fields is inductance and magnetic flux and inductance. Okay, so it turns out that people wondered, if currents can create magnetic fields, can we use magnetic fields to create currents? And the answer is yes, but it's not quite as simple as just, you know, you have a magnetic field and a current is created. It's not magnetic fields that directly create currents. It's changing magnetic fields which will create a current. Okay, and so static magnetic fields, they don't create currents. They will exert a force on a current, but they won't create a current. Okay, so if you have a wire and it's not attached to a battery or anything like that, you just have a wire and you just bathe this wire in a magnetic field. There's no current in the wire. You just bathe it in the magnetic field. Well, the magnetic field is not going to create a current in that wire. Okay, so people wondered, is this possible? But if you take this wire and you put it in this magnetic field and the magnetic field grows or shrinks, then it does induce a current. Okay, and this is called inductance. All right, and magnetic flux is part of this idea of inductance. All right, this was actually discovered by Faraday, and also at the same time by another physicist called Henry. Okay, and the way to understand this is you have to picture a loop of wire in a magnetic field. Okay, and so again, one of these diagrams which is kind of hard to draw, so I've tried to give you a couple of different perspectives here. If you look at the loop of the wire directly on edge, okay, so, you know, like here's my hand and you're looking directly on edge, it just looks like this flat line. Okay, so that's what you're looking at here. I tried to give it a little bit of perspective. Okay, but this is a loop of wire, but you're looking at it on edge, and so all you see is just kind of like a line there. Okay, now if you turn a little bit like this, you know, here's the loop of wire and you turn a little bit, then you'll see it in perspective, and that's what I'm trying to show there. Okay, so you've got these B field lines like this, and you've got this loop of wire, and the loop of wire makes an angle theta. It's oriented at an angle theta to the B field like that. All right, you can define from these quantities here this thing called a magnetic flux. Okay, and here is the formula for the magnetic flux. It's basically equal to the strength of the B field, the area of the loop. Okay, so the loop, I mean, it's just a wire, but the loop is creating like an area. All right, and so the area that's created by the loop that goes into the magnetic flux, also multiplied by the orientation. Okay, and the idea behind a magnetic flux is kind of like the loop is capturing some of the lines of the magnetic field. Like some of these lines of the magnetic field, they're stuck inside the loop, and some of the lines of the magnetic field are outside of the loop. And so the magnetic flux is kind of a measure of how much the loop encapsulates or captures B field lines. Okay, and so you can see here, like I didn't draw other more magnetic field lines outside of the loop, but you can imagine there are maybe more B field lines up here like that. But the loop is just capturing these four B field lines. They're captured inside of the loop, and that's called the magnetic flux. Okay, it's basically equal again to the strength of the field, the area, and the sine of the angle that the loop makes with the magnetic field. Okay, now at this point there's nothing about there's nothing about any kind of induced current. Okay, if the B field doesn't change and A doesn't change and theta doesn't change, there's a flux there, but there's going to be no current inside the wire. All right, so I guess I should just point out this diagram. I kind of alluded to it, but you see here, here's the B field. Here's the B field being captured by that loop. When it's perpendicular, that's when you're going to get the most B field lines. When the loop is actually along the line of B. Okay, it's right along the lines of B. Well, then there's no flux captured. Okay, and so now, how are we going to be able to induce a current? Okay, and the answer is Faraday's law. If you calculate this flux and this flux doesn't change over time, then there's no current. But if the flux does change over time, the rate at which this flux changes over time, okay, so that's like your delta phi. Phi is the symbol for flux, obviously. So it's the delta phi by delta t. It's how fast the flux is changing. The faster the flux changes, the more potential is induced in that wire. Okay. By the way, in this context, it's often called an electromotive force. Okay. We tend to sometimes refer to batteries as providing a potential, and in this case, an electromotive force. But as far as we're concerned, it is a voltage. Okay. And so this is a perfectly legitimate way of writing it. All right. It's just in case you see it somewhere else referred to as an electromotive force. It is a voltage. Okay. So if the flux doesn't change over time, then there's no voltage. Okay. But if the flux does change over time, the faster the flux changes over the time, the more voltage is actually induced. Okay, so once again, it's not the magnetic. A static magnetic field is not going to do anything. Okay, you actually have to have a changing magnetic field giving rise to a changing flux, and it's that changing flux which gives rise to a voltage, and the voltage will then create a current inside the wire. This is known as Faraday's law. You'll notice that there's a negative there, and that negative actually has to do with the direction, and it's known as Lenz's law. Okay, and Lenz's law just says that the direction in which the current is created in the loop, because there's going to be this change in flux, and the change in flux is going to be, because maybe the magnetic field is changing. I'll show you different ways in which the flux can change in a second, but let's assume that the magnetic field is changing. The induced current in the wire is going to try to oppose the change in the magnetic field. And so this is what I'm trying to show here with Lenz's law. So here we have a B field, and say the original B field was all the way out to the end there like that, okay? But it's shrinking over time. This B field's getting weaker and weaker and weaker. And so you can see my little delta B there shows how much that B field has shrunk, okay? Well, what happens is in the coil here, or in that loop, you're going to induce a current. The current is going to be induced so that it would create a delta B in the opposite direction to the shrinking B field. So in other words, the current that's created in the wire tries to create a B field which opposes the shrinking of the B field. Okay, and this is known as Lenz's law. Okay, it's a little bit subtle. But it does say, what the direction is of the current. As the B field shrinks, Is the current going to be induced this way, or is the current going to be induced the other way? And the answer is the current is induced such that it opposes the shrinking of the B field. It tries to push the V field back out. By circulating this way, it creates like a delta B this way, which tries to push the B field back out. Okay, not a big deal, but there it is. Okay, so well, there you go. This is known as Faraday's law. And let's go back up here to Faraday's law again. Technically speaking, I've been saying the B field change, the B field change, but it's not so much the B field that has to change to create a potential. It's this flux that has to change. And there's three things that go into the flux, calculating the flux. What are they? Well, there's the magnetic field, there's A, and there's theta. And so you can change your flux by changing B, or you can change your flux by changing A, or you can change your flux by changing theta. Now, how would that work? Well, how would you change B? Let's scroll down here to where I talk about that. Okay, how could you change B? Well, one way you could change B is by just pulling a magnet out of a loop. Okay, so you have that loop there, and we've got the magnet inside the loop. So here's the loop, and here's the magnet inside the loop. And if you just pull the magnet out, what you've effectively done is you've removed the magnetic field, and then of course B is going to change. Okay, so one way to change B is to just pull the magnet out of the loop. Okay, or whatever's causing the B field, usually like a magnet or whatever. Okay, so that's one way to change your flux. Another way to change a flux is you have that A, which is the area of the loop. Okay, like that. And you could just deform the loop. You could have the loop like that, but maybe you can squish it out. And by squishing out the loop, you change A, and then by changing the area that the loop makes, you could also be changing the flux. But the more typical way is to just change theta, because by changing the orientation, you're going to change, theta from 0 to 90 degrees, and that'll change like the sign from 0 to 90 degrees. Okay, so those are the three different ways in which the flux can change. All right, and typically, like in anything that you're building, like in an electric generator, which I'll discuss in a second, it's the theta that changes, and all you do that is by just rotating the loop. Okay, by rotating the loop, you'll actually change your theta, and that's how the flux changes. All right. One more equation before we start to do some problems. The previous equation that I gave you was actually the flux for a single loop. And what is a solenoid? A solenoid is n loops. Okay, so you could think of a solenoid as not just having area A, but having area A for each one of the n loops that are in the solenoid. And so the flux for a solenoid is magnetic field, but the A here is multiplied by n, where n is the number of windings, okay, sine theta, okay? So that's why I put the n and the A together, because there's a cross-sectional area to the solenoid, but because each winding contributes its own A to the cross-sectional area, the total cross-sectional area, if you want to think that way, is going to be n times A. Okay, we'll need this equation a little bit later, but that's basically the flux for a solenoid. Okay, now we're ready to do a problem here. Okay, so there's no reason why the loop of wire has to be a circle. If it is, then its area would be pi r squared. Okay, but it can be a square, and or actually a rectangle. I said square here, but a rectangle. So I have a loop of wire, and it's going to be 1 centimeter on one side by 3 centimeters on the other side. Okay, and this loop is made to rotate 250 times per second in this 500 millitesla field. Okay, and I want to know what is the induced potential. All right, and so you have to think about this. We've got two different orientations here. Okay, where's my picture? Here are the two orientations. The loop at one instant in time, it's going to be like this. And then the loop at another instant in time is going to be like that, because you got to think this loop is, here's my loop, and it's rotating like that. It's continuously rotating in there. And so, at one point it's going to be at 90 degrees, then it's going to be at 0, and then it's going to be at 90 again, and then it's going to be at 0. And if you think about this, you think about this loop rotating in there, going from 90 to 0, 90 to 0. In any one complete rotation, it will go from 0 to 90 degrees or 90 to 0 4 times. Okay, in other words, it'll go from this orientation to that orientation, and then it'll go from that orientation back to that, and then it'll go from that orientation back to that in one cycle. Okay, so over here in our problem, the first thing we're going to note is that it only takes a quarter of a revolution to go from 90 degrees, which is your maximum flux, to 0 degrees, which is your minimum flux, or vice versa. Okay, that's only a quarter of a revolution. Okay, so here we are, and there, that's only a quarter. That's a half of a revolution, and if I did more, there's the 3/4, and then finally you're back again. So every quarter revolution, you're either going from 0 to 90 or 90 to 0. Okay, so there we go. Now in 1 second, we'll go from so in 1 second we'll go from 0 to maximum, or maximum to 0, not 250 times, but 4 times 250 times. Okay, so think about that a little bit. Basically, you're going from, because every quarter turn of your loop, you're going from a max to minimum, or minimum to maximum. Okay, so this move from minimum to maximum happens 4 times for every rotation. There's 250 rotations per second, and so you're going to have 1,000 times that you're going from minimum to maximum. Okay, and so our delta t and our v is equal to delta t is going to be 1,000th of a second. Okay, and our delta phi, that is from our maximum to the minimum. Well, the minimum is 0 because when sine of 0, when theta is equal to 0, sine of 0 is 0. Okay, so the minimum flux is going to be 0. The maximum flux happens at 90 degrees, so that's just going to be basically your magnetic field times A times sine of 90 degrees, which is 1. The magnetic field, I told you, was 500 milliteslas, or 0.5 teslas, and the area now is the area of the loop, but it's a square loop, so it's just length times width, so it's 1 centimeter by 3 centimeters, or 0.01 meters by 0.03 meters, because we got to work in MKS, and that gives us 3 times 10 to the minus 4 meters squared. And putting that into our flux, B, 0.5 teslas, A, 3 times 10 to the minus 4 meters squared, and that gives us a flux of 1.5 times 10 to the minus 4 Tesla meters squared. So there you go. There are the units of flux. They're Tesla meters squared. And so now that's your maximum. Your minimum is 0, so your delta phi is going to be 1.5 times 10 to the minus 4 Tesla meters squared. It takes only 1,000th of a second for it to make that change in flux. And so if you plug that in there, here's our 1,000th of a second down here, 10 to the minus 3. It turns out that you get 0.15 volts. Okay, so the voltage that's going to be induced around this loop will actually be 0.15 volts. Okay, and now the next question is, do these units work out? Okay, namely, if you take a Tesla meter squared and divide it by a second, does that really give you a volt? Because I just said that it gives you a volt, and it's MKS, so it should give you a volt, but does it actually work out to a volt? And so let's take a look at that. Let's find out. Is a volt really equal to a Tesla meter squared per second? So the best way to understand the Tesla is always from Lorentz's law. And remember from Lorentz's law that a Tesla is basically a Newton per amp meter. Okay, just to remind you, if you have 1 meter of wire carrying 1 amp in a 1 Tesla field perpendicular, that's going to give you 1 Newton of force. Okay, so if we put that in there for our Tesla, so we have a Newton per amp meter, and we multiply everything out, we get to this form right here. Okay, but a Newton meter, that's a joule. Okay, because that's work. If you do a Newton, if you have a Newton of force and you push something 1 meter, that's basically 1 joule of work. So 1 Newton meter is a joule. And an amp, remember what an amp is, that's a measure of current. It's 1 coulomb traveling past you every second. So 1 amp is a coulomb per second. So if you put that in here, basically you're going to get that an amp times a second is just a coulomb. And so Newton meter on top gives you a joule, an amp second gives you a coulomb, a joule per coulomb. That's exactly what a volt is. Okay, these units are getting pretty tricky. Okay, and there's like a bunch of different ways in which you can derive them and show that they work out. I'm not going to do all of them, but yeah, they do work out. Okay, so there you go. That's why I said amazing, because it's not something that you would have, seen intuitively from the beginning. Okay, so so there you go. This is basically Faraday's law. All right, and now we can actually describe two very important devices that something crashed there. Two very important devices in um, our modern world, and they are the electric motor and the electric generator. Okay, so actually, Ampere's law is uh, uh, the law which governs how an electric motor works, and Faraday's law is kind of the opposite of Ampere's law. It's how an electric generator works. So let's just take a look at those two devices just qualitatively. And so here, an electric motor, how does it work? Well, basically we have a loop of wire here like that, and we don't just apply the current in one direction, we actually apply a current in uh, an alternating current. So one moment the current is traveling one way, and then we turn it around and we have it travel in the other direction. Of course, by Ampere's law, this means that you're going to get a magnetic field, but the magnetic field itself is going to alternate in direction. So that's why I have this magnetic field, and it looks kind of funny there because it's pointing this way, and then it's also pointing the other way. And you go, well, which one is it? Well, it depends on which way the current is going, and I also have the current bouncing back and forth. So as the current bounces back and forth, 1 minute it's going one way, and then the next minute it's going the other way. The B field is going to bounce back and forth, back and forth. Okay, so 1 minute the B field is one way, the next minute the B field is the other way. Well, let's put a magnet in the vicinity of that B field. Okay, and so 1 minute the magnet is going to want to orient itself one way. The next minute it's going to want to orient itself the other way. In other words, it's going to want to flip. Well, you get the mechanism right to make sure that it doesn't just flip back and forth, that it actually rotates. And what you're going to do is, as you keep alternating the current here, you alternate the magnetic field. And as you alternate the magnetic field, you turn the magnet. And there you go. There's an electric motor. Okay, so I don't know if you've ever taken apart electric motors. I used to love taking things apart as a kid, which is probably why I wound up in physics. But I took apart electric motors, and sure enough, you could see these magnets in there and coils of wire. And the coils of wire, when they have these currents traveling through them, they will force the magnets to turn. Okay, usually it's done in some other ways, but this is good enough to really explain what's going on. Okay, usually they have the magnetic fields stationary and they cause the coils to turn, but it's still the same idea. Okay, so there you go. This is how an electric motor works, and it's based off of Ampere's law. So how does a generator work? Well, you know what? It's the exact opposite. It's the same diagram. Okay, but this time what you do is, rather than applying the current, you rotate the magnet. But as the magnet rotates, it changes the flux through the coil, or through the loop here. And as the flux changes, you get an alternating current. You induce a current. Okay. Well, when the flux is changing one way, the current turns one way, and when the flux is changing in the opposite direction, you get the current going in the other direction. Okay. And so an electric motor run backwards, that is, instead of you applying a current to it and it turns something, you turn it, it will induce a current, and it becomes an electric generator. Okay, so the same electric motor and electric generator, they're really the same device. It just depends on what are you inputting. Are you inputting a current? Then you'll get out mechanical energy. Do you input the mechanical energy, that is, you rotate the magnet, then you get output a current. Okay, so just thought I'd mention those because at this point we can understand the two. All right. So last topic with magnetism, Faraday's law together with Lenz's law. The two really are not separated. I mean, Faraday's law says that the changing flux creates a potential, and the Lenz's law just says what direction that potential is in. Okay, but the two together actually make it possible to create yet another device known as an inductor. Okay, and that's what we're going to study to the end of this video. Okay, so what is this inductor? An inductor basically is a device which uses a B field to resist a change in a current. And this is sometimes useful in electronics because what you're going to do is, if you get a current going, you don't want the current to abruptly shut off. Okay, and to prevent a current from just shutting off abruptly, you actually use this inductor, which has this B field, which keeps the trying to push the current. Remember Lenz's law, what it says? If the B field tries to change, it actually induces a current which tries to oppose that change in the B field. So the B field kind of keeps the current always going. Okay, it tries to avoid a change in the current. Okay, of course, if you don't keep giving it energy, then it will eventually damp out, and you'll see that with our my RL circuit that we'll study in just a second. But basically, that's what an inductor is. It's a device which uses a B field to try to resist any kind of changes in the current in a circuit. Okay. And how does this work? Well, here's a little diagram, a little a circuit diagram of a current. There's no battery here. There's just a current, and this current is traveling through the solenoid. And guess how you make a good inductor? You use a solenoid. So this current is traveling through this inductor, and when the current travels through the inductor, it establishes a B field in there. Okay, and what winds up happening is, and now this is an ideal situation, if there's no resistance in the wire, the B field makes sure that the current just keeps going. Okay, so of course you got to get the current going to start with. Okay, if you just hook up a solenoid, and you just tie the two ends of the solenoid together, there's not going to be a current. You got to get the current going. But once the current is going, if you close the circuit this way, the B field here will make sure that that current keeps going and it doesn't stop. Again, ideally no resistance. If there's a resistance, it will eventually damp out, and we'll look at that in a second. But if there's no resistance, the B field here will keep the current going. And you go, why? Why does that happen? Well, imagine that the current tries to slow down. If the current tries to slow down, then that changes the B field. The B field tries to decrease. But if the B field decreases, a changing B field induces a current. And it'll induce a current which counteracts the attempt of the current to decrease. Okay, so the current tries to decrease, but that causes a change in the B field, which tries to increase the current back to where it was. And so it kind of keeps itself at an equilibrium. Okay, that's roughly how an inductor works. Okay, and so let's take a look at how we define the inductance of an inductor. Okay, so basically there is a current traveling, and if the current tries to change, okay, then it actually creates a voltage inside of the wire. All right, and the degree to which the changing current actually creates a voltage, a potential, that's called the inductance. Okay, that's actually given a measure. Okay, now why you want to define it this way, you'll see in just a second, but let's just see if we can understand the physics here. We got this current going. All right, and the current tries to change over time, tries to make a change over time, and what happens is because of the B field, okay, it creates a current to counteract it so that the current can't change, and so a changing current actually leads to some potential, which then, and you know that a potential will actually create a current. Okay, now the degree to which the changing current tries to create a potential in that circuit that I just drew, the degree to which that happens, that's known as the inductance, and it's given the symbol L. Okay, now this might be a little bit mysterious to you. Let's see what the relationship is between this and Faraday's law, because after all, it's Faraday's law which is responsible for pushing that current back up when it tries to decrease. Okay, again, the current tries to decrease, that tries to change the magnetic field. The changing magnetic field means that there's a changing flux, and a changing flux means that there's a potential which boosts the current back up. Okay, so let's start off with Faraday's law, and let's see if we can actually get it into this form, okay, so that we can identify the inductance for a particular device. And you can almost guess the device, it's a solenoid. All right, and so if we take the magnetic flux for a solenoid, remember I gave you that formula earlier, it's B times not just the cross-sectional area, but the cross-sectional area times the number of loops, because each loop adds its own contribution to the flux, times the sine of A, okay, or sorry, sine of theta, and the orientation of the loops. Let's assume that the loops are perpendicular to the magnetic field, which is what you get in a solenoid anyhow. Okay, I mean, you can make the solenoid kind of a weird shape, but in a proper solenoid where the loops are like this, okay, they're coiled like that, like I drew above, the magnetic field is perpendicular to the to the area that each loop creates. Okay, so theta here is 90 degrees and sine of theta is 1. And so you can write that as just B times NA. Now, the other thing is we're talking about a solenoid, and there's a relationship because of Ampere's law of the magnetic field in the solenoid due to the current that's applied. Okay, and so that was one of the formulas I gave above from Ampere's law. The magnetic field is basically mu naught times N over L, the density of the windings, multiplied by the current. Okay, and we can plug that back into here and get the flux for a solenoid. Okay, and plug that back into here, and then plug that into here, and that's what we have right here. Okay, now this doesn't look like the formula we had above, but it is. It's delta the flux. Here is the flux. Okay, that's delta the flux divided by delta t. I just pulled the delta t out front so that it's a little easier to say. And then this is delta, and everything in the square brackets here is the flux. Now what's going into that flux? Well, B is going into the flux, and here's B. Okay, for the solenoid, mu naught N over L times I. That's your B for the solenoid. And then it's multiplied by A, but A enhanced N times. So there's your NA like that. And you can just rearrange this, and it looks like this. Okay, and now you'll notice that N, the number of windings in the solenoid, that doesn't change. You know, you're not gonna go into the circuit and unwind it, so N remains fixed. The area of the solenoid, we're gonna leave that alone. We're not gonna take the solenoid and squish it or anything like that. Okay, so the cross-sectional area of the solenoid will stay the same. The length of the solenoid will stay the same. So everything here stays the same. And mu naught, that's just a constant. I is the only thing that can change. Okay, so we can pull all of these constants out front, and you just have I. And so now you can write Faraday's law for a solenoid as this quantity out front times delta I over delta t. Okay, so once again, you know, in that diagram that I had earlier, let me just go back to this diagram here. I agree this is a little bit subtle, so it's worth, you know, thinking about this. In this diagram, there's this solenoid, and this solenoid has a current going through it. Okay, now if the current were to try to change, that would be like a delta I over some time delta t. Okay, that would cause a change in B, and the change in B would then counteract and cause a corresponding change in I to try to restore the original I, so that I stays at equilibrium. You know what it's like? It's like you know, like a pendulum, you know, and it's down here. If you displace the pendulum to one side, well, then it's going to swing back. Okay, so so the B field always wants to restore the current back to I. If you try to you know, increase it a little bit, the B field will decrease it back to its original value. Or if you try to decrease I, then it'll increase it back to the original value. Of course, when you increase I, in that moment when you increase I, there's the B field is creating this potential, that this V, which then creates a current to counteract and bring I back. Okay, and that's what this equation is all about. All right, down here, if there's a change in I over some time, then it's going to create some change in V. For the solenoid, we actually have the relationship between the rate at which I changes and the induced V, and it's this quantity here. Okay, now if you look at this equation here and you look at the definition of what inductance is, so this here, think of this as the definition. I know I don't have L isolated on the one side, but this equation here tells you what you mean by L. L, the inductance, is the constant of proportionality between the rate at which I changes and the voltage that it induces. Okay, so if you have a very weak inductor, then you're going to need a very rapid and big change in I over time to get very little V. That's a poor inductor. A very good inductor will give you a lot of voltage for just a very little change in I over time. Okay, so that's the way to think about inductor. It's like, how much voltage do you get for a given rate of change in I? Okay, and for the solenoid, there it is. It's this quantity right there, okay? Because here's your change in I over time. That's the rate at which I will change over time. And there's the voltage that's induced. And the quantity out in front is the inductance. So, ta-da, there is the formula for the inductance of a solenoid, okay? How does it go? Well, the more windings there are, the more inductance there is. The bigger the cross-sectional area, the more B field you have in there, because the bigger the area, the more B field you're capturing, the bigger the inductance. And the shorter the solenoid, in other words, the more dense the windings are, the bigger the inductance. And of course, mu naught is just that permeability of free space. Okay, there it is, and we're going to use this to solve a problem in just a second. But remember, with a solenoid, you can actually put a ferromagnet in the middle, put a ferromagnetic core in it, and if you put a ferromagnetic core in it, you actually change that mu naught, you enhance the mu naught. And so if there's a ferromagnetic material inside the solenoid, you replace the mu naught with mu r times mu naught, where this mu r is just known as the relative permeability of the ferromagnetic material. We saw a problem like that before. Okay, and we're actually going to use the same ferrite material with a mu r of 2,300. It's basically the enhancement of the permeability because of the presence of the ferromagnetic material. Okay, just one comment about this formula. You'll notice this n squared there, and you go, why is it n squared? And the reason is that oftentimes inductance is called self-inductance, and you go, why is it called self-inductance? And so you have to think about it this way: each loop interacts with every other loop. Okay, so it's like the loops are like influencing one another. How? Well, each loop, because it carries a current, creates a B field. Okay, so the loops are creating the B field. But at the same time, the B fields created by those loops, they're going to induce a current in the other loops if the B field changes. Okay, so it's every loop is interacting with every other loop. One loop will create a B field, which another loop will feel if that B field changes. Okay, and that's why it comes in as an n squared. Okay, so if you have 10 loops and each loop is interacting with 10 loops, that's 10 times 10 loops, and there you go. There's your n squared. Okay, well, let's use that formula to calculate the inductance for a solenoid. And so here we have that mu r is equal to 2,300 for nickel, zinc, ferrite. This is the same material, ferromagnetic material that we discussed earlier when we made an electromagnet out of a solenoid. Okay, and what is L for the solenoid made with 100 windings of wire, 5 centimeters long, with a diameter of 1 centimeter filled with nickel, zinc, ferrite? Okay, so let's go through it. Well, I tell you that there are 1,000 windings, so capital N, the number of windings is 1,000. Okay, I tell you that the length of the solenoid is 5 centimeters long, so L is 5 centimeters, so 0.05 meters. Okay, and the solenoid, I mean, you can make square solenoids. That is, they're still wrapped, but they're, like every time you make a loop, you actually make a square loop like that. Okay, so you could do that, but in this case, we have round loops. Okay, and I'm telling you that the diameter of the solenoid, that is from one end to the other end, is 1 centimeter. So that means that it's got a radius of half a centimeter. Okay, so the diameter of the solenoid is 1 centimeter, and so the radius is half a centimeter, or 0.5 centimeters, and you got to convert that to MKS, so it's 0.005 meters. Okay, so there's the radius of the solenoid, and we need the cross-sectional area, so the cross-sectional area is pi r squared. Remember when we were working with the continuity equation with fluids, and we had round pipes, the cross-sectional area was pi r squared. It's the same idea there. Okay, and so if we plug in the numbers to get the area first, that's pi, and r is 0.005 squared, and so that gives us a cross-sectional area of 7.85 times 10 to the minus 5 meters squared. And now we're ready to plug all our numbers into the equation for the inductance of a solenoid. It's going to equal mu r times mu naught. It's not just mu naught because of the presence of the ferromagnetic material. It's mu r times mu naught, n squared a over L. Okay, so there's the mu r, the relative permeability. That's that 2,300 for nickel, zinc, ferrite. There's mu naught. Okay, 1.26 times 10 to the minus 6 Tesla meters per amp, times, there's our n squared, 1,000 squared, multiplied by the cross-sectional area, which we just calculated, 7.85 times 10 to the minus 5 meters squared, divided by the length, which was 5 centimeters, or 0.05 meters. Okay, and it works out to 4.55 Tesla meters squared per amp. And you go, what the heck is a Tesla meter squared per amp? Well, we could live with that unit. It's a measure of inductance, but because one of the physicists that worked on this was called Henry, we call it a Henry, okay? And actually 1 Henry is pretty big. It's quite a lot of inductance. But that ferromagnetic material, that's really what's doing a lot of the enhancing here, okay? And so the inductance of that particular solenoid is 4.55 Henries, okay? Uh, Now, this Henry, the units in electromagnetism, they go wild, okay? And we're going to have to see that, and we're going to work with Henrys a little bit. So it's good to see how a Henry relates to some of the other units. And so another way to understand a Henry is to express it as a volt second per amp. And you go, well, how does that work out? If you go back to the equation that defined inductance, we had V is equal to L delta I over delta T. If you just do a unit analysis on this, potential is measured in volts, so there's your volt, okay? Delta T is measured in time, so there's your second. I is measured in amps, so there's your amp. And if you just isolate the L on one side here, you're going to get that an L is, which a Henry is going to be a volt second per amp. Okay, so this is yet another way to think of a Henry. So one way to think of a Henry is a Tesla meter squared per amp, and that came out from our calculation of the inductance of a solenoid, and that's the same as a volt second per amp. And the other thing, the other way you'll see this, and this is probably the most important way to see it, is remember that an ohm, which is a measure of resistance, 1 ohm is a volt per amp. And so we have a volt here and we have an amp there, so a volt divided by an amp is an ohm. So another way to think of a Henry is as an ohm second. Okay, so the 1 Henry is equal to the same as 1 ohm second. All right, and this is actually not that bad. I mean, a lot of people usually think of Henrys as ohm seconds, and the reason is that an inductor is a little bit like a resistor. Okay, not quite. I mean, there's some significant differences, but at least in one respect, you can think of an inductor as a resistor, because what does a resistor do? Well, a resistor impedes current. Okay, so you remember that one of the first circuits I drew was a battery and a resistor, and the bigger the resistor was, the less current you were going to get. Okay, that was Ohm's law. Okay, why? Because the resistor resisted current. Well, an inductor doesn't quite resist current. It's what it does is it resists changes in current. Okay, and so it's a little bit like a resistor because it'll resist the change in the current. But if there's a current there, it says, okay, I'm happy with that current. But if you try to increase that current or you try to decrease that current, it undergoes that dynamic that I mentioned earlier, and it resists that change. And so that's why it's not surprising that there's the ohm in there, but it's a change over time, and that's why there's a second in there. Okay, so a Henry is an ohm second. All right. All right, so there's a lot of properties to inductors, but we're not going to go off and do a full electronics course, and I'm just going to mention them to you. They're pretty easy to remember, so there's not very deep. But really, the circuit that I want to end this with is an LC circuit. But let's just mention a few other properties of inductors. The first thing is, like when we had resistors and capacitors, inductors yet another electronic device. Well, remember resistors? Resistors in parallel and resistors in series. Resistors in series, they add. Inductors do too. Okay, so if you have two inductors in series, like one inductor right after another, the equivalent inductance is just the sum of the two inductances. Okay, so they're just like resistors, and the same thing when they're in parallel. Okay, so when you have two inductors in parallel, their equivalent is the sum of the reciprocals. So 1 over the L equivalent is equal to 1 over L1 plus 1 over L2. Okay, so the way to remember this is just remember that for series and parallel, inductors and resistors work exactly the same way. Okay, that is series add, parallel reciprocals add. Okay, we had the capacitors. We had an RC circuit. Well, you know what? You can have RL circuits too. Okay, now if you remember the RC circuit, and that was in the previous video, in the RC circuit, you charged up the capacitor, and then you allow the capacitor to discharge through a resistor. If there was no resistance there, if the wire were like a perfect wire, the capacitor would instantly discharge. I mean, all the electrons on the one side would just flop over to the other side and that's it. But if there's a resistor, what does the resistor do? It limits the current, so it just allows a slow trickle of current to come across, and then the the capacitor takes some time to discharge through the resistor. Okay, well, it's the same thing with an RL circuit. So if you go back up here, when I first introduced this circuit, all the way up here, I said this was an ideal circuit, and I said to you the current will never speed up or slow down here. The current will stay constant in this. Okay, that's because the B field will cause it to do that. But also you have to assume that there's no energy being lost in the wires. Okay, now that doesn't happen in reality because every wire has a little bit of resistance. But if the wires had no resistance, the current would just travel through this wire all the time, and the current would never increase or decrease, because if it tried to increase, the B field would bring it back. Okay, or another way to think about it is any fluctuations of the current, which always occur because of whatever, the B field would always restore it back to its equilibrium value. Okay, but in reality, there's always a little bit of resistance in the wire, and so what happens when you have an RL circuit? And so what's an RL circuit? Well, here it is. This looks a lot like the RC circuit, only instead of a C there, I have an L there. Okay, and you'll notice that the switch can be in one of two positions. If I put the switch in position number 1, the battery is going to start a current going. Okay, never mind this little leg here. Okay, because if the switch is in position 1, then that little leg there is irrelevant, and you just get a current traveling through the resistor. That gets the current going. Okay, and that current won't go off to infinity, because why? Because there's a resistor there that's going to limit it. Okay, and then when you switch the switch to position number 2, what's going to happen? Well, the current that's going through there, you'd think, well, there's no battery, the current will just stop. No, because the B field in here tries to keep the current going. It tries to keep the current going, but there's energy being lost in the resistor, and so the current will exponentially decay. So just like the RC circuit, where it was the charge in the capacitor which charges up and then discharges, Q goes to a maximum and then it decays away. Here it's not a charge, it's actually the current. So when the switch is in position 1, the current builds up. It doesn't build up right away. It can't jump right away, because what does the inductor do? It resists a change in the current. So even when the current starts to build up, if there's no current and the current starts to build up, the inductor goes, nah, I really don't like that. Eventually it will, because there's energy in the battery, and it's going to push that current through, but it doesn't allow an immediate jump in the current. If that inductor weren't there and you close that switch, the current would immediately jump to its maximum value. Okay, but because there's an inductor there, the current has to exponentially approach its maximum value. Then when you close the switch, if you close the switch and there were no inductor there, the current would immediately stop. But because there's an inductor there, and an inductor resists a change in the current, the inductor is going to try to keep that current going, just like you saw above. But there's the resistor there, which will eventually slow it down. Resist this current, and it'll eventually slow it down, and it'll go to 0. So I'm not going to do any derivation. I'll just give you the formulas, because here they are. They look just like the formulas for a charging capacitor charging up or capacitor discharging. This is the situation where the switch is in position 1. In position 1, you start with no current, and the current builds up to a maximum. Okay, the maximum current that is achieved is exactly what comes out of Ohm's law. The maximum current is just going to be V divided by R. That's just Ohm's law. Okay, but you don't achieve that maximum current right away. You start at 0 current and you build up over time. Okay, because the inductor won't allow an instant change. And so your equation looks like this. Okay, so this equation, if you compare it to the equation for a capacitor charging up in the RC circuit, you'll see that it looks the same, except that in there we had Q's and here we have I's. So for the RC circuit, you're looking at charges building up. For the RL circuit, you're looking at currents building up. Okay, and the current builds up. The other thing that's different, of course, is that the time constant tau, I mean there's no c here, so the time constant is different. The time constant in this case is equal to L divided by R. Okay, so there you go. There's the time constant for that. I'll show you that it actually has the right units in a second. Now, what if you put the switch in position 2? Well, in position 2, this is the equivalent of the discharging. Okay, so now the inductor is trying to push that current through the resistor, but the resistor slows it down, slows down the current by dissipating away the energy as Joule heating, and so you'll have an exponential decay, and there's your exponential decay. Okay, I didn't even draw the graph, but it looks just like the graph that you saw for an RC circuit where it decreased down to zero. From starts off at some I naught and then decays down to zero at very long times. It's useful to look at the units of tau. Okay, the units of tau have to be seconds because you got to have seconds over seconds here. And for the RC circuit, you would see that tau worked out to be seconds. Let's see that it works out to be seconds here. So here, the units of tau have to be the units of inductance divided by the units of resistance. And remember, I said probably the best way to think of a Henry is as an ohm second. So you have ohm seconds on top divided by ohms. The ohms cancel out and you're left with seconds, and that's what you expected. Okay, so let's do a quick problem with this, and then we'll get to our last circuit, which is the probably the most interesting circuit. It's the LC circuit. Okay, so we have a 50 millihenry inductor. That's a typical size, millihenries on microhenries. Okay, a Henry, 1 Henry is quite a bit of inductance. Okay, you can make them, but that's a lot of inductance. Okay, so a 50 millihenry inductor is placed in series with a 50 kilo ohm resistor. Okay, and again, 50 kilo ohms, that's a typical resistor too, and a 10 volt battery. So we have all three in series, and this is equivalent to the switch being in position 1. And so what is the maximum current through the circuit? That's question number 1. And how long does it take from when the switch is closed until it reaches until the current reaches reaches 99% of its maximum? Okay, so basically, what are we looking at here? We're looking at this circuit here, but we're looking at this circuit with S in position 1. Okay, when S is in position 1, we have 3 devices: the battery, the resistor, and the inductor, all in series. Okay, so here we have a 50 millihenry inductor in series with a 50 kilo ohm resistor and a 10 ohm battery. What is the maximum current? Well, the maximum current, it's like the inductor isn't even there. Okay, once the B field has been built up and the current has reached its maximum, the inductor is happy. It says, well, there's a current going through me, and it's not increasing, it's not decreasing, and as long as the current stays the same, the inductor says fine. Okay, remember, it's the changing current which leads to the changing magnetic field, which leads to the counter current that tries to counteract the changing current. That's what's going on. Okay, and so it's just Ohm's law. Okay, yeah, there's an inductor there, but it's, the maximum is just Ohm's law. It's V over R, and so you have 10 volts divided by 50 kilo ohms. Kilo is 10 to the 3. Okay, and so that turns out to be 0.2 times 10 to the minus 3 amps, or 0.2 milliamps, okay, or 200 microamps if you want to write it that way, okay. But 0.2 milliamps, this is a small current, okay, a small current. Now the next part says, you know what, we want to know how long from when I close the switch, okay, and start the current going. So the current is at 0, I close the switch, and the current starts to wind up until I reach 99% of the maximum current. Okay, well, for this one, we want to use this equation right here. Okay, we want to use that equation. All right, and the ratio of I over I naught. I didn't give you I, and I mean, you could use this for your I naught, but I didn't give you I. I just said that the ratio I to I naught is 99%. In other words, I has reached 99% of the maximum. 0.99. Okay, so if you plug that into the equation above, you get that 0.99 is equal to 1 minus e to the minus t over tau. Okay, then rearranging this, because we want to solve for t, okay, we do know tau. I just haven't plugged in the numbers yet, but we want to solve for t. So isolate the exponential here e to the minus t over tau is going to equal 1 minus 0.99. That's just a rearrangement of the previous equation, which is equal to 0.01. Okay. And now you say, well, what do I do with this? Well, you remember what we did with decibels, and you remember what we did with the same equation, but with the RC circuit, we had to take the natural log of both sides. So if we take the natural log of both sides, that's ln on your calculator. Take the natural log of both sides. This, taking the natural log of e to the minus t over tau, just strips out the minus t over tau there, like that. Okay. And the natural log of 0.01, well, you can do that on your calculator. It turns out to be negative 4.61. So you get that minus t over tau is negative 4.61. Now the negatives drop out, and that basically tells you that the time you have to wait is 4.61 taus. And you say, but do I know tau? And you do, because I told you what L is, and I told you what R is, and tau is equal to L over R. So L is 50 millihenries, so that's 50 times 10 to the minus 3 henries. R is 50 kilo ohms, so that's 50 times 10 to the 3 ohms. And if you divide this out, that's 1 times 10 to the minus 6 seconds. 10 to the minus 6 is a microsecond. So the time constant here is really short. It's only 1 microsecond. Okay, so this is very fast. And so the current, it's not instant. It's fast, but it's not instant. It would take 4.61 milliseconds to build up from 0 to 99% of its maximum value. Okay, 99% of its maximum value. You can measure this on an oscilloscope. Okay, obviously a millisecond is way too short for human things. So if you hooked up something else, like, I don't know, an LED or something like that, to try to see this, I mean, you wouldn't. It would, to the human eye, it would just seem instant. But to an oscilloscope, yeah, you'd be able to see that this is actually taking 0.461 milliseconds. You just set the oscilloscope to trigger on 99% of what you expect I naught to be, and you'll get the trace, and from the trace you'd be able to see that it took 0.461 milliseconds to build up. Okay, last circuit that we're going to study is an LC circuit. Okay, so the previous one was an LR circuit, so we had a resistor and an inductor together, and you know what the resistor is going to do. It's just going to bleed away the current. So the inductor is trying to keep this current going. The inductor is trying to keep the current going, but the resistor bleeds it away, and you get the exponential decay. Okay, but what happens if you put an L and a C circuit, an L and a C together in series in a circuit? Okay, and you might even ask the question, what happens if you put L, C, and R together? Okay, well, we're not going to study the LCR, but the LC gives you, believe it or not, an oscillator. Okay, it'll actually oscillate with a certain frequency. I won't derive that for the 112. I will for the 102, but in another video. Okay, I'm actually going to do some calculus to show you that that's true. But the LC actually turns out to be like a simple harmonic oscillator, which is amazing. Okay, the LCR turns out to be a damped harmonic oscillator. Okay, so in the lab that we did where we had the damped harmonic oscillator, the LCR circuit actually acts like a damped harmonic oscillator, whereas the LC by itself acts just like a harmonic oscillator. So, like I said, I'll derive that for the 102. But for both of you, how do we understand this? How can we understand that this LC circuit is actually going to act like an oscillator? So here it is. Here's my LC circuit. Here's my inductor L, and here's my capacitor. Okay, and we got to start this thing going. Okay, so like a pendulum will bob back and forth, but if the pendulum is just sitting there, it's not bobbing back and forth. Someone's got to come by and pull it to the side and let go, and oscillates like that. Okay, and so you got to start this whole thing going by either charging up the capacitor or getting a current going through the inductor, one or the other. But you got to start it going. And I said, what, this little V here. I guess it should have been a battery, not a voltmeter, but that little V there. I'm just saying, I'm just going to charge up my capacitor. Okay, so you can imagine taking the capacitor out of the circuit, applying a voltage, charging it up, and then putting it back into the circuit. Okay, so we start off by charging out the capacitor. So here we go. Here's step number 1. Okay, and you have this capacitor here, and one part of it has a positive charge, one part has a negative charge. And of course, what does it like to do? It wants the current, using the conventional current, which goes from positive to negative. The current wants to flow from the positive to the negative there, like that. Okay, and it actually can, because it sees a wire there and it goes, hey, I've got this closed circuit, I can flow through there. Okay, now if this inductor weren't there, this were just a straight wire and these were perfect wires with no resistance, the current would go, let's just all go at once, we'll do it all at once, and bloop, the capacitor would instantly discharge. Okay, but there's this inductor there, and remember what an inductor does, it resists a change in current. And so the capacitor first has to do some work to get the current going, but it does. As the capacitor discharges, a current starts to build up. Whoa, it's going to kick me out. No, I don't want to get kicked out. Cancel. Okay. Uh-oh. Sorry, guys. One sec. There we go. Okay. I guess our the Moodle session ended and it said kick me out, but we're almost done anyhow. So, as the capacitor discharges here, it does so by creating a current. But the current, as it passes through the inductor, starts to build up a magnetic field. So the capacitor, in order to get that current going, discharges, and eventually it's totally discharged. But in doing that, it got a current going. And that current, when it was going through the inductor, which tried to resist it, but got pushed through there, built up a magnetic field, built up a magnetic field, built up a magnetic field. And now we're in the situation where we have a current and it's being pushed through the inductor by the magnetic field. The magnetic field in there said, and the inductor says, no, I don't want this current to slow down. I don't want this current to stop. Keep it going. And so the current keeps going. And you know what's going to happen? Yeah, the capacitor is discharged, but not for very long. Because what happens is as the magnetic field collapses, the inductor keeps pushing that current, and now the capacitor starts to build up with a positive charge on this side and a negative charge on that side. Well, that continues until the inductor just has no more energy left. The magnetic field is totally collapsed, and you're back to the situation where there's no magnetic field in the inductor, and the capacitor is totally charged up. But now what does the capacitor do? The capacitor says, I want to discharge. I want to discharge by sending my current back the other way. And so if you want the analogy to the pendulum, we swung from one side here to the other side, and now we're going to swing back. Okay, so originally we had, the top plate positively charged, but now we've swung around to the other side, and now the bottom plate is positively charged. And these positives say, I want to go to the other side. Of course, they do that through the inductor. The inductor builds up a magnetic field, and there's a current going, and it keeps pushing them through until we're back to step one. And this just keeps repeating. Okay, so you're going between the inductor having no B field and the capacitor being charged up. The capacitor discharges, creates a current through the inductor, and now there is a built-up B field. The built-up B field keeps the current going, and that charges up the capacitor, and they go back and forth like that. They go back and forth with a certain frequency. Okay, so I'm not going to prove it here, but here it is. Here is the frequency at which the oscillation occurs. Now, this I just put there because that's what's going to come out of my derivation for Physics 102. But for Physics 102 and 111, this is the linear frequency, and that's what you would measure in the lab. Okay, so if you build this LC circuit, what you would discover is that it oscillates. Okay, and you could hook it up to an oscilloscope, and you would see that the voltage goes up and down, up and down, up and down, up and down like that. It'll actually oscillate, and it oscillates with a frequency f, which is equal to 1 over 2 pi, the square root of L times C. Okay, so there's the linear frequency of the oscillating LC circuit. All right, now let's do an example with this. Okay, so the first thing is, where would you use this oscillating circuit? So this is basically like a resonance. Now, we didn't get to do the vibrating string lab in the physical lab, but there, when you had the sonometer, you had that pickup mic, which was receiving it, but you also had this driver, and the driver, you could tune the frequency on the driver, and when the driver had a frequency which matched the frequency of the string would start to vibrate at that frequency, and those frequencies were discretized. Okay, that's exactly what happened here. If you build this LC circuit and you don't charge up the capacitor, and you don't put a current through the inductor, you just leave them alone. You say it's going to sit there. Well, not quite. If you attach an antenna to anywhere on the circuit, radio waves are going to come by, and these radio waves are going to cause the electrons to jostle back and forth. And if these electrons jostle at the same frequency at which the LC circuit oscillates, you're going to have a buildup of the oscillation inside the circuit. You're going to get a resonance, and that's what a radio is. An LC circuit is the simplest possible radio. If you're interested in this sort of stuff, you can actually look up how to build crystal radios. Okay, they're basically LC circuits. Okay, so that's my question here. We want to build a radio to listen into an FM to listen to FM radio. Okay, and in particular, we want to listen to 94.5 megahertz. Okay, so that's what we want to tune into. What size inductor do we need if our capacitor is 47 picofarads? Okay, now pico is very small, but you do need a small capacitor for this one. Okay, and so the question is basically we're going to use this equation here. We're going to use this equation here. Okay, and the frequency. I told you it's 94.5 megahertz, and I tell you the capacitor. We want to solve for L. Okay, we want to solve for L. So if we take that equation and we square it, we get that F squared is equal to 1 over 4 pi squared L over C. That's to get rid of that square root. And then just rearrange it to isolate L on the one side. So basically divide both sides by F squared, multiply both sides by L, and you get this equation here. All right. And now we're ready to plug in, but we just have to be careful. You haven't seen pico before. Okay. You've seen micro, and that's 10 to the minus 6. That's a million. You've seen nano, which is 10 to the minus 9. Pico is 10 to the minus 12. Yeah, there are really tiny capacitors that are down in the 10 to the minus 12 farads, and these are basically picofarad capacitors. So this capacitor is 47 picofarads, and pico there you're going to replace with 10 to the minus 12. Okay, 10 to the minus 12. And so substituting in the numbers in MKS, there's 4, pi squared, 3.14 squared. F, the frequency is 94.5 mega, and mega is 10 to the 6 squared. Okay, and the capacitor is 47 pico, is 10 to the minus 12. Okay, so if you work this out, this works out to 6 times 10 to the minus 8 henries, or if you want to, convert it to nanohenries, just move the decimal over 1 to the left here, and that's going to make minus 8 minus 9 there. So it's 0.6 times 10 to the minus 9 henries, and 10 to the minus 9, that's a nano, so it's 0.6 nanohenries. Okay, and so if you take a 47 picofarad capacitor, which you can actually buy. Okay, 47 picofarad seems to be one of the standard size capacitors, and you put it in series with a 0.6 nano Henry inductor. You would be tuning into 94.5 FM. Okay, that's kind of cool. All right, so there's how you build a crystal radio. Here's another example. So a typical size inductor is 50 microhenries, and a typical size capacitor is 50 nanofarads. And we build an LC circuit, and at what frequency does it oscillate? I just wanted to show you, what typical size what frequencies you get with typical size capacitors and inductors. So you plug in these numbers, and I'm just going to skip the details here. You wind up with 100 kilohertz. Okay, so 100 kilohertz. That's below the FM radio. I think FM starts at 550 or 570. I'm not sure which, but it's basically long wavelength. Okay, below the AM radio. All right, so there you go. Now, last thing we're going to do with LC circuits. A minute ago, I made this analogy between the oscillation of the LC circuit and the oscillation of a string and a sonometer. And is there more to that analogy? And the answer is yes, and it's a rather remarkable thing. So that's why I want to end with this last point, okay? So it's insightful to see what kind of frequency you get if we build our LC circuit using parallel plate capacitors for our capacitor and a solenoid for our inductor, okay? You could build inductors in other ways. Solenoid is the more typical way. You can build capacitors in other ways, but parallel plate is the most typical. Okay, so we kind of abstract them, but let's go back to the way we the way I showed you could design capacitors and inductors. So if you go back to the capacitor, a capacitor, parallel plate capacitor, has a capacitance C given by this formula here. So what's this formula? A is the area of the two plates, and D is the distance between them. Now I had to call this AC because I need to distinguish this from the cross-sectional area of the inductor. So AC is the area of the two plates in the capacitor. They're a distance D apart. I don't have any dielectric in there. Okay, I didn't put a dielectric. So all I have here is the permittivity of free space. Okay, and now for our inductor, we're going to use a solenoid. Here's the solenoid, and from above, that's going to equal the permeability of free space, mu naught, and squared the cross-sectional area of the solenoid. So I call that one AL divided by L, which is the length of the solenoid. Okay, and just not to confuse things, I just repeated that here. Okay, so AC is the area of the parallel plates, and D is the distance between it. AL is the cross-sectional area of the solenoid, and L is the length of the solenoid. Okay, now if we put these two here into the equation for the frequency, we substitute them in for C and L, we get the following. Okay, whoops. Okay, there we go. Okay, we get the following. All right. Well, I did it in steps. Sorry, I did it in steps. So here's the equation we're substituting into. We're substituting into this equation here for LC. Okay, so I did it in steps so that we don't get confused. So I first took L and C and multiplied them together. Okay, and if I take L and C and multiply them together, I get that epsilon naught times the mu naught. Okay, so the permittivity multiplied by the permeability of free space multiplied by this n squared ACAL over DL. Okay, like that. All right. Now the next thing is that if you take a look at the formula, it's like F is equal to 1 over 2 pi square root of LC. So I still, not to put this in the denominator, just still keep life easy. I just said let's multiply by 2 pi times the square root of LC. So take all of this and put that in there. Okay. So then we have the 2 pi, and I'm going to factor out the epsilon naught mu naught, but it's under the square root because everything's under the square root. And then we get this term here. Okay. And what is this term here? Well, it's that n squared ACAL over D times L. Okay. Well, I'm going to rearrange the terms a bit. You might say, why are you rearranging them this way? And you'll see in a second. And you see that pi there? I'm going to put the pi with this square root over here. I'm going to basically take the 2 and the square root of the epsilon naught mu naught. I'm going to put them together in the front here. I'm going to take that pi and I'm going to put it with this one. See the n squared there? That's under a square root, so that just becomes an n out in front. So I've got a pi times an n times the square root of the 2a's divided by dl. Okay, and you go, what the heck is this? Well, you know what? It really doesn't matter exactly what that is. Let's just think about what the units are of that thing. Okay, well, the units of the two areas, they're meters squared. And the units of the two lengths, D and L, they're both lengths, they're meters. And so if you go into that square root and you just ask, what are the units of that square root? Well, that one's going to be meters squared, that's meters squared, and that's meters, and that's meters. So on top, you're going to have meters squared times meters squared. You get meters to the 4, and on the bottom you have meters squared. So meters to the 4th divided by meters squared, that's meters squared. But then you take the square root of that, and it just turns out to be meters. So whatever this thing is, it's just some length. And you go, what is this length? Well, I don't know. But we can call it the characteristic length of the LC circuit. And so I'm just going to define the characteristic length of this LC circuit as that pi, which is I decided to lump in with this, the n, the number of windings, it was n squared under the square root, but when it came out it's n, multiplied by this quantity here. Okay? And so now this LC, it's just some characteristic length to the LC circuit. And you go, what is this characteristic length? It's kind of the net effect of all the geometrical factors that go into building the LC circuit. Okay, it just, the way I put it here is that this length just encapsulates all of the geometrical properties. And so basically, if you just take all of that mess up there and just replace it with LC, that 2 pi, the square root of LC is just equal to 2 times the square root of the epsilon naught mu naught multiplied by that characteristic length of the LC circuit. Okay, and if we put that into this equation here, we get 1 over 2 square root of epsilon naught mu naught times LC. And now, I know this is a little bit long, but we're almost done. And now I'm going to say, look, I'm going to say, let me think of this 1 over the square root of epsilon naught mu naught. Let me think of that as a v, like some velocity. Well, if I do that, look at what this becomes. This equation becomes F is equal to V 2 times that characteristic length. And that equation should look familiar, because you know what that equation is? That's the equation for the fundamental frequency of a string. And at this point you're going, well, what? Where's the string in the LC circuit? How is this LC circuit at all like a string? Well, it is, because the string vibrates at a frequency, a characteristic frequency, its fundamental frequency, and the LC circuit does as well. Okay, so there's something about that, fact that they're both resonance resonance systems, that means that there's a homology between them, and here it is. Okay, an isomorphism between them. Okay, and at this point you go, well, okay, that LLC, okay, that characteristic length of the LC circuit, that's kind of like all the geometry of the capacitor and the inductor all kind of lumped into one thing. Okay, there it is. But what's this V? Well, the V was equal to this, and let's plug in the numbers here. V is equal to 1 over the square root of epsilon naught mu naught. So we plug in the numbers for the permittivity and permeability of free space. And the permittivity has units farads per meter. The permeability has units henries per meter. Okay, let's look at the units first, because we want to make sure that we get the right units here. I mean, I called it V, but do we know that this is a velocity? Well, let's see if the units work out. Okay, well, if you have a let's just do the farad times the Henry first. So you have a farad times a Henry. A farad, measure of capacitance, is a coulomb per volt. Okay, and a Henry is an ohm second. Okay, and remember that an ohm is a volt per amp. That's from Ohm's law. Ohm is a volt per amp. And so if we put that all in here, so here's the coulomb per volt for the farad, and here's the volt per amp times the second for the Henry. And don't forget that an amp is just a coulomb per second, coulomb flowing by per second. And so we put that in here, okay? And so we have coulomb divided by coulomb per second times the second. The coulombs cancel. The second in the denominator of the denominator comes up to the top and gives you second squared. And so a farad times a Henry is a second squared. But we didn't just have farads and Henrys up here. We had farads per meter and Henry per meter. And so if you take a farad per meter and a Henry per meter and you multiply them together, you get a second squared per meter squared. But that's in the square root of the denominator. So if you put that second squared per meter squared under a square root sign and you do 1 over that, you take the reciprocal, that's going to give you meters per second. It's a velocity. This quantity here, okay, I mean, I anticipated knowing the answer that it's going to be a velocity, but this quantity here, 1 divided by the square root of mu naught times epsilon naught, or epsilon naught times mu naught. So that quantity is a velocity. And you might wonder, what is that velocity? So we know it's going to come out per meter squared. Now, if we work out the numbers, it actually turns out that that velocity is 2.99 times 10 to the 8 meters per second. And if you look at it for a second and you recognize it, that's the speed of light. And so you go, what? How in the world is this LC circuit? The LC circuit is basically like a string tied down at both ends, okay? A standing wave, where the velocity of the wave is the speed of light. And the answer is that, guess what? Electromagnetic waves are light, or light are electromagnetic waves. And so the reason I did what I did was I took the frequency of the LC circuit and I purposely massaged it into what looks like the frequency for a standing wave, the fundamental frequency for a standing wave. The reason I did that was to identify this V, and that V turns out to be the speed of light. And that's exactly right. Okay, the reason you're getting the speed of light there is because Maxwell, later physicist. We won't do his stuff because it's too advanced. He discovered that oscillating electric fields give rise to, because of Ampere's law, oscillating B fields. But oscillating B fields, because of Faraday's law, give rise to oscillating electric fields, which give rise to oscillating electric fields, oscillating B fields, oscillating E fields, oscillating B fields. This oscillating, creating an oscillator, B, E, B, E, means that you basically have wave behavior, but not just in one thing, but in both E fields and B fields, okay? It turns out that radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays, they're all electromagnetic waves of different wavelengths. Okay, and it's even more interesting. Okay, I didn't write this down, but since we're here, look at this again. Okay, do you remember what the velocity was for waves on a string? It was the square root of the tension divided by the linear mass density. So you always had these two competing things. You had the tension, which the greater the tension, the more velocity you got for your waves, but that competed against an inertial property, which was like your linear mass density, and the heavier the string was, the slower the waves, because the harder it was to cause to oscillate. Okay, so the tension increased the velocity, and the weight, the mass density, decreased it. Well, you know what? That's square root of T over mu. That's exactly like this. Okay, it's kind of like the permittivity and the permeability. They're both like the T and the mu, but now this is the tension and the density of free space. Okay, empty space. And I know that sounds weird, that even empty space has properties, but yeah, empty space has properties, and it has a property with respect to E, and it has a property with respect to B, and it's those two properties together that actually set the speed of the waves in that medium. Medium in quotes, because it's empty. Okay, and so that's the amazing thing about electromagnetic waves. So I just wanted to end. There's no problems with this, but I just wanted to end, since we did study LC circuits, I did want to end this by showing the relationship between the permittivity of free space, that is the ability of free space to sustain electric fields, the permeability of free space, which is the ability of free space to sustain magnetic fields, and the speed of electromagnetic waves. Okay, there you go. Okay, that's the end of this lecture for Physics 112. This is the end of electricity and magnetism. For Physics 102, there's going to be a short lecture where I derive some of the properties for the circuits, for the RC circuit, for the LC circuit, and for the LR circuit. Okay, I'm going to actually prove some of the things using a little bit of calculus. Okay, thank you.